For over a century, astronomers have been playing a cosmic game of hide and seek with the outer solar system. Every few decades, something doesn't add up. Orbits behave strangely. Objects appear where they shouldn't. Calculations point to invisible hands pulling strings in the darkness beyond Neptune. Sometimes these hunches lead to triumph, like when mathematical predictions guided telescopes straight to Neptune in 1846, or when Clyde Tombaugh spotted Pluto's faint dot in 1930. But sometimes they lead nowhere, like the decades-long search for Planet X that turned up empty. Now, in 2025, the hunt is on again. Except this time, the evidence is stronger, the mathematics more compelling, and the mystery deeper than ever before. The story begins not with a discovery, but with an anomaly. Actually, dozens of anomalies. Out past Neptune, in the frozen wastes where sunlight barely reaches and temperatures hover just above absolute zero, there's a population of icy worlds called trans-Neptunian objects. The ghosts beyond Neptune. The Kuiper belt stretches from about 30 astronomical units from the Sun, where Neptune's orbit ends, out to roughly 50 AU. 1 astronomical unit equals the distance from Earth to the Sun, about 93 million miles. So we're talking about a region that starts nearly 3 billion miles from home. At these distances, the Sun looks like just another bright star in the sky. Temperatures plunge to around 40 Kelvin, cold enough that nitrogen and methane freeze solid. Any world out here exists in perpetual twilight, receiving less than 1,000th the sunlight that Earth gets. This is where Pluto lives, along with thousands of other icy bodies, ranging from mountain-sized chunks to dwarf planets hundreds of miles across. But the Kuiper belt is just the beginning. Beyond it lies the scattered disk, a region where objects follow highly elliptical orbits that take them far above and below the plane where the planets orbit. These scattered disk objects have been gravitationally kicked by Neptune at some point in their history, sent careening into elongated paths that can stretch hundreds of AU from the Sun. Some take thousands of years to complete a single orbit. Eris, one of the largest known dwarf planets, lives out here with an orbit that ranges from 38 AU at closest approach to 97 AU at its farthest. Sedna, discovered in 2003, pushed the boundaries even further with a perihelion of 76 AU and an aphelion of 937 AU, taking roughly 11,400 years to orbit the Sun once. Then there are the extreme trans-Neptunian objects, or ETNOs. These are the weirdos that started the whole Planet 9 hypothesis. They're defined by having semi-major axes greater than 150 AU and perihelia beyond Neptune's orbit at 30 AU. In simpler terms, their closest approach to the Sun is still beyond Neptune, and their orbits are enormous. These objects spend most of their time in the outer darkness, only occasionally swinging through the inner solar system relative to their full orbital paths. Objects like 2012 VP 113, discovered by Scott Shepard and Chad Trujillo, have perihelia around 80 AU and semi-major axes over 250 AU. Sedna remains the poster child, with its absurdly distant perihelion that keeps it permanently detached from Neptune's gravitational influence. What makes these ETNOs interesting isn't just their extreme orbits, but how those orbits are oriented. In a solar system shaped only by the 8 known planets, you'd expect these distant objects to have randomly oriented orbits. Their arguments of perihelion, the angle that describes where in their orbit they make their closest approach to the Sun, should be scattered all over the place. Same with their longitudes of ascending nodes, which describes where their orbital plane crosses the plane of the solar system. Random orientations, random angles, like throwing darts at a dartboard. Except that's not what we see. In 2014, Chad Trujillo and Scott Shepard published a paper noting that several ETNOs had suspiciously similar arguments of perihelion. They all seemed to reach their closest approach to the Sun in roughly the same region of space. The odds of this happening by chance were small, but not impossible. Maybe it was just a coincidence. Or maybe there was some observational bias, since these objects are easiest to discover when they're closest to the Sun and brightest. But the pattern was intriguing enough to warrant attention. 2 years later, in January 2016, Konstantin Batygin and Mike Brown from Caltech took the analysis further. They looked at 6 ETNOs with the most reliable orbit determinations and found not just one clustering pattern, but several. The arguments of perihelion clustered near 0 degrees. The longitudes of ascending nodes are also clustered together. And perhaps most strikingly, the orbits were all tilted in similar ways relative to the solar system's plane. Running the numbers, they calculated that the probability of all these alignments happening by random chance was about 0.007%, or roughly 1 in 14,000. Those are odds that make astronomers sit up and pay attention. Batygin and Brown didn't stop at identifying the pattern. They ran computer simulations to figure out what could cause it. They modeled the outer solar system with and without an additional planet, tweaking the hypothetical planet's mass, orbit, and position to see what would happen to the ETNOs over millions of years. What they found was striking. If you placed a planet with about 5 to 10 times Earth's mass in an orbit with a semi-major axis of 400 to 800 AU, highly elliptical and tilted relative to the other planets, it would gravitationally shepherd the ETNOs into exactly the clustered configuration that observations showed. The simulations didn't just explain the clustering, they predicted it. This wasn't a cosmic accident. This was the signature of something massive pulling strings from the darkness. The hypothetical planet, dubbed Planet 9, would be unlike anything else in the solar system. With 5 to 10 Earth masses, it would be a super-Earth or a small ice giant, larger than Earth but smaller than Uranus and Neptune. Its orbit would be wildly eccentric, ranging from perhaps 200 AU at closest approach to over 1,000 AU at its farthest, taking between 10,000 and 20,000 years to complete one orbit. At those distances, it would be incredibly faint, possibly magnitude 22 or dimmer, which is beyond the reach of most telescopes even today. If it exists, it's hiding in a vast swath of sky, moving slowly enough that picking it out from background stars requires painstaking comparison of images taken months or years apart. The reaction from the astronomy community was mixed. Some embraced the hypothesis enthusiastically, seeing it as a natural extension of how Neptune was discovered using similar gravitational clues. Others were skeptical, pointing out that the sample size of ETNOs was small and potentially biased by observational limitations. After all, these objects are extraordinarily difficult to find. They're small, dark, and distant, reflecting almost no sunlight. Discovery depends on large-scale surveys that repeatedly image the same patches of sky, looking for objects that move against the background stars. Surveys like the Panoramic Survey Telescope and Rapid Response System, or PANSTARRS, and later the Dark Energy Survey, have been responsible for finding most ETNOs. But these surveys don't cover the whole sky uniformly, and they're more sensitive to objects in certain regions. Could the clustering be an artifact of where and how we're looking? That question drove much of the research over the following years. Astronomers scrambled to find more ETNOs, hoping that a larger sample would either strengthen the clustering signal or wash it out as a statistical fluke. Every new discovery was scrutinized. Does its orbit fit the pattern? Does it strengthen the case for Planet 9, or weaken it? The debate became heated at times, with papers published arguing both sides. Some researchers ran their own simulations and found that alternative explanations, like the combined gravitational influence of smaller objects in the Kuiper belt, might produce similar clustering without needing a large planet. Others pointed out flaws in those alternative models, arguing that the math still pointed toward Planet 9. What complicated matters further was the realization that some of the ETNOs didn't fit the pattern. As more objects were discovered, it became clear that not all of them had aligned orbits. Some had arguments of perihelion pointing in completely different directions. Some had orbital planes tilted at odd angles. If Planet 9 was responsible for shepherding the ETNOs into alignment, why weren't all of them affected? Battigan and Brown argued that this was actually expected. Planet 9's gravity would affect objects differently depending on their initial orbits and how they interacted with Neptune in the distant past. Some would be captured into the aligned configuration, others would be scattered into different orbits. The presence of outliers didn't disprove Planet 9, it just meant the dynamics were more complicated than a simple cause and effect relationship. By 2020, the number of known ETNOs with well-determined orbits had grown to over a dozen. Statistical analyses continued to show clustering, though the significance varied depending on which objects were included and how the data was analyzed. Some studies found clustering probabilities of less than 1%, others found closer to 10%. The question of observational bias remained contentious. If surveys were more likely to discover ETNOs in certain parts of the sky, that could artificially create the appearance of clustering, even if the true distribution was random. Disentangling real gravitational effects from observational artifacts required careful modeling of survey detection efficiencies, a complex task that different research groups approached in different ways, leading to different conclusions. Then came the strangest twist of all. In 2021, astronomers started finding ETNOs that seemed to be in resonance with the hypothetical Planet 9. Resonances occur when two orbiting bodies have orbital periods that are simple ratios of each other, like 2, 1 or 3, 2. These relationships lock the objects into stable configurations where they repeatedly encounter each other at the same points in their orbits. The moons of Jupiter are locked in resonances with each other. Pluto is in a 3, 2 resonance with Neptune, orbiting the Sun 3 times for every 2 Neptune orbits. Resonances are powerful gravitational mechanisms that can shepherd objects into specific orbits and keep them there for billions of years. Battigan's team ran simulations suggesting that if Planet 9 exists, it should capture some ETNOs into resonances, particularly high-order resonances like 3, 1 or 4, one where the ETNO orbits the Sun 3 or 4 times for every 1 Planet 9 orbit. When they checked the known ETNOs, they found several candidates that seemed to fit these resonant relationships. The orbits matched the predictions almost perfectly. But here's the problem. To be in resonance with Planet 9, you need to know where Planet 9 is and what its orbit looks like. And we don't. The simulations could place Planet 9 in a range of possible orbits, each producing different resonant configurations. The fact that some ETNOs seemed to match resonant predictions was tantalizing, but it wasn't proof. It could still be coincidence, or it could mean the simulations were on the right track. The Caltech search and its frustrations. Mike Brown, one half of the team that proposed Planet 9, is no stranger to the outer solar system. He's the astronomer who discovered Eris in 2005, the dwarf planet that triggered Pluto's demotion from planetary status. He's found dozens of trans-Neptunian objects over his career, including some of the largest and most distant known. If anyone has the experience and tools to find Planet 9, it's Brown and his colleagues. And they've been looking hard. The search for Planet 9 isn't like looking for a lost set of keys. It's more like searching for a single needle in a haystack the size of a continent, except the needle might be in a completely different haystack or might not exist at all. The challenge is threefold. Planet 9 is faint, it's moving slowly, and we don't know exactly where it is. Brown's team has been using some of the world's most powerful telescopes to systematically search regions of the sky where Planet 9 is most likely to be based on their models. They've used the Subaru telescope in Hawaii, which has a wide field of view perfect for scanning large areas of sky. They've analyzed data from other surveys. They've looked at infrared observations from space telescopes. And so far, nothing. The frustration is palpable in interviews and papers. Brown has publicly stated that Planet 9 should have been found by now given the amount of effort that's gone into the search. The fact that it hasn't shown up is starting to raise uncomfortable questions. Is Planet 9 fainter than expected? perhaps because it's smaller or farther away than the models predict? Is it hiding in a region of the sky that hasn't been searched thoroughly yet, maybe near the plane of the Milky Way where background stars make detection harder? Or is it possible that Planet 9 doesn't exist at all, and the clustering of ETNOs has some other explanation? One possibility that researchers have explored is that Planet 9 might be in the most distant part of its orbit right now, at aphelion, where it would be faintest and hardest to detect. If its orbit is as eccentric as the models suggest, it could be over 1,000 AU from the Sun at the moment, possibly even farther. At that distance, even a Neptune-sized planet would be incredibly dim, and a 5 Earth-mass planet would be near the limits of detectability for current telescopes. The search might simply require more time and more sensitive instruments. Another complication is proper motion. Even though Planet 9 would be moving slowly from our perspective, taking thousands of years to orbit, it's still moving. That motion has to be accounted for when comparing images taken at different times. If Planet 9 moves even a tiny amount between observations, it might appear as a different object in each image, making it hard to confirm as a real planet rather than a background star or artifact. Automated detection algorithms can miss slow-moving objects, especially if they're faint and near the detection threshold of the telescope. Brown and Batygin have refined their models over the years, incorporating new data and improving the simulations. In 2021, they published updated predictions for Planet 9's orbit, narrowing down the search area, but also acknowledging the uncertainties. Their best estimate placed Planet 9 at a distance of around 400 to 500 AU right now, with a mass closer to 5 Earth masses rather than 10. These adjustments were based on the growing catalogue of ETNOs and better understanding of how Neptune's gravity affects the outer solar system. But even with a refined search area, the task remains enormous. The region of sky where Planet 9 could be is dozens of square degrees, and every square degree has to be imaged multiple times to catch the planet's subtle motion. The Subaru telescope has been the workhorse of the search. Its hyper-suprime cam can image a field of view about 1.5 degrees across, which is large by telescope standards. Brown's team has conducted systematic surveys, imaging the same regions of sky repeatedly to build up a catalogue of moving objects. The process is painstaking. Each image has to be compared with previous images to identify objects that have shifted position. False positives are common: asteroids passing through the field, background stars that vary in brightness, or instrumental artifacts that mimic real objects. Every candidate has to be vetted, followed up with additional observations, and often discarded. Despite the challenges, the search has produced valuable science even without finding Planet 9. Brown's team has discovered numerous new ETNOs, adding to the catalogue and improving the statistical analysis of orbital clustering. Some of these new discoveries have strengthened the case for Planet 9, fitting neatly into the predicted orbital distribution. Others have been outliers, complicating the picture, but providing data points that help refine the models. Each new ETNO is a piece of the puzzle, and the puzzle is slowly coming into focus, even if the centerpiece, Planet 9 itself, remains missing. Then there's the question of infrared detection. Planets emit heat, especially large planets that still retain warmth from their formation. Even billions of years after forming, a 5 Earth-mass planet would have some residual heat in its interior. In the infrared part of the spectrum, where heat radiation is visible, Planet 9 might be slightly brighter than in visible light. NASA's Wide Field Infrared Survey Explorer, or WISE, conducted an all-sky survey in infrared and detected thousands of asteroids, brown dwarfs, and other objects. Brown's team searched the WISE data for Planet 9, but came up empty. The non-detection placed limits on how bright Planet 9 could be in infrared, which in turn constrains its temperature and mass. If Planet 9 is too cold or too small, it might not emit enough infrared radiation to stand out in WISE data. More recently, attention has turned to the upcoming Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope. Set to begin operations in the mid-2020s, the Rubin Observatory will conduct the most comprehensive survey of the night sky ever attempted. Its 8.4-meter mirror and 3.2 gigapixel camera will image the entire visible sky every few nights, creating a time-lapse movie of the universe. If Planet 9 exists and is within the survey's detection range, Rubin will almost certainly find it. The observatory's automated data processing will identify moving objects, including slow-moving ones like Planet 9, and flag them for follow-up. It's a game-changer for outer solar system science, and many astronomers are betting that if Planet 9 is real, Rubin will be the one to spot it. But there's a nagging worry. What if Rubin doesn't find it? What if the survey completes, catalogues thousands of new trans-Neptunian objects, maps the outer solar system in unprecedented detail, and Planet 9 still doesn't show up? That outcome would force a reckoning. It would mean either Planet 9 is so faint or so far away that even Rubin can't detect it, or it doesn't exist. And if it doesn't exist, then the clustering of ETNOs needs a new explanation. The alternative explanations that keep getting weirder. Not everyone is convinced that Planet 9 is the answer. Over the years, alternative explanations have been proposed, some conventional, some downright bizarre. Let's start with the mundane ones. The simplest alternative is that the clustering is a statistical fluke amplified by observational bias. When you survey the sky for faint, distant objects, you're more likely to find them when they're brightest, which happens when they're closest to the Sun and to Earth. For ETNOs with eccentric orbits, that means discovering them near perihelion. If surveys happen to find several ETNOs near perihelion in the same general region of the sky, it could create the appearance of clustering even if the true distribution is random. It's a bit like fishing in a pond and catching most of your fish from one side, because that's where you cast your line most often. It doesn't mean all the fish are on that side, just that your sampling is biased. Several research groups have tried to quantify this observational bias by simulating surveys. They create fake populations of ETNOs with random orbits, then simulate how a survey would discover them given real-world constraints like telescope sensitivity, sky coverage, and weather. If the simulated detections show clustering similar to what we actually observe, it would suggest the real clustering might be an artifact. Results have been mixed. Some studies find that bias can explain part of the clustering, but not all of it. Others find that even accounting for bias, the clustering is still statistically significant. The debate hinges on assumptions about the true population of ETNOs, which is unknown, creating a circular problem. You need to know the real distribution to assess bias, but you can't know the real distribution until you correct for bias. Another alternative involves the Kuiper belt itself. What if, instead of one large Planet 9, there are many smaller objects in the outer solar system whose combined gravity creates the clustering? This idea, sometimes called the collective gravity hypothesis, proposes that a massive disk of smaller bodies beyond Neptune could gravitationally nudge ETNOs into aligned orbits. Computer simulations have tested this idea with mixed success. The challenge is that you need a lot of mass in the outer solar system to replicate Planet 9's effect, possibly several Earth masses worth of material spread across a wide region. Current surveys suggest there isn't enough mass in the Kuiper belt to do this, but if there's an unseen population of objects too faint to detect, it might be possible. The collective gravity hypothesis has a major problem, though. Most simulations show that it would take an unrealistically large amount of mass, more than seems plausible based on models of solar system formation. When the solar system formed, the outer regions beyond Neptune were gravitationally stirred by the migrating giant planets, scattering material and preventing it from coalescing into large bodies. The mass that remains in the Kuiper belt today is just a fraction of what was originally there, most having been ejected into interstellar space or the Oort cloud. Packing enough mass into the trans-Neptunian region to mimic Planet 9's effect seems inconsistent with what we know about how the solar system evolved. Then there are the truly weird ideas. In 2020, a pair of physicists proposed that Planet 9 might not be a planet at all, but a primordial black hole. These hypothetical black holes, with masses ranging from asteroids to planets, could have formed in the early universe and survived to the present day. If one happened to be captured by the Sun's gravity billions of years ago, it would orbit just like a planet, exerting gravitational influence on nearby objects. The appeal of this idea is that a black hole would be nearly impossible to detect directly. It wouldn't reflect sunlight or emit heat. Its only signature would be gravitational, exactly what we're seeing with the ETNOs. The problem is that primordial black holes are entirely theoretical. There's no confirmed evidence they exist at all, and invoking one to explain Planet 9 feels like replacing one mystery with an even bigger one. Still, the black hole hypothesis gained enough attention that astronomers actually tried to test it. If Planet 9 is a black hole, it might be detectable through gravitational lensing. When a massive object passes in front of a background star, its gravity bends the star's light, causing a brief brightening. Primordial black holes in the 5 Earth mass range should produce detectable lensing events if they're out there. Researchers analyzed data from microlensing surveys, but found no candidates matching Planet 9's expected properties. That doesn't rule out the black hole hypothesis entirely, but it makes it less likely. For now, most astronomers treat the primordial black hole idea as an entertaining thought experiment, rather than a serious contender. Another exotic proposal involves a captured rogue planet. Planets can be ejected from their home star systems through gravitational interactions, becoming free-floating worlds drifting through interstellar space. Early in the solar system's history, when the Sun was still part of its birth cluster surrounded by other young stars, it could have gravitationally captured a passing rogue planet. If that planet ended up in a distant eccentric orbit, it would look exactly like Planet 9. The idea is plausible in principle. Computer simulations show that captures are possible, though rare. The captured planet would need to lose energy somehow to become bound to the Sun, perhaps through interactions with the gas disk that existed in the early solar system, or through a close encounter with one of the giant planets that slowed it down just enough to be captured. The rogue planet scenario has an interesting implication. If Planet 9 is captured, its composition and properties might be different from the Sun's native planets. It could have formed in a different stellar environment with different chemical abundances. Its atmosphere, if it has one, might have unusual isotopic ratios or unexpected molecules. If and when Planet 9 is found, spectroscopic observations could test this idea by looking for signatures that don't match what we'd expect from a planet born in our solar system. Of course, this assumes we can get good enough data to measure its composition, which would require a much closer look than just detecting it as a faint dot. One more alternative that's gained traction recently is the idea of multiple smaller planets instead of one large one. What if there are 2 or 3 Mars-to-Earth-sized planets lurking in the outer solar system, their combined gravitational effects creating the ETNO clustering? Simulations have shown this could work under certain conditions. The planets would need to be in specific orbits, spaced apart in just the right way to collectively shepherd the ETNOs into alignment. The advantage of this scenario is that smaller planets might be easier to miss in surveys, explaining why nothing has been found yet. The disadvantage is that it requires fine-tuned initial conditions, which seems unlikely unless there's some dynamical mechanism that naturally produces such a configuration. Every alternative explanation has strengths and weaknesses. The observational bias argument is hard to dismiss entirely, but struggles to explain all the clustering patterns. The collective gravity of smaller Kuiper belt objects requires implausibly large amounts of mass. Primordial black holes lack observational evidence. Captured rogue planets are possible, but would require a specific set of circumstances in the solar system's early history. Multiple smaller planets need fine-tuning. Planet 9 remains the simplest explanation that fits the data, but simple doesn't always mean correct. The outer solar system has surprised us before, and it might surprise us again. The orbital mechanics that don't lie. Let's get into the nitty-gritty of what makes the ET-NO orbits so compelling. Orbital mechanics is one of the most precise branches of physics. Given enough observations of an object's position over time, you can calculate its orbit with extraordinary accuracy. Newton's laws and Kepler's equations have been tested and refined for centuries. When astronomers say a group of orbits is clustered, they're not making a vague observation. They're measuring specific orbital parameters, 6 numbers that completely define an orbit's shape, size, and orientation in 3-dimensional space. The first parameter is the semi-major axis, which defines the size of the orbit. For ET-NOs, this ranges from 150 AU to over 500 AU or more. The second is eccentricity, which describes how elliptical the orbit is. A circle has eccentricity 0. The more stretched out the ellipse, the closer the eccentricity gets to 1. ET-NOs have eccentricities around 0.6 to 0.9, meaning their orbits are highly elongated. The third is inclination, the tilt of the orbit relative to the plane where the planets orbit. Most planets orbit in nearly the same plane, but ET-NOs can have inclinations of tens of degrees. The next 3 parameters describe the orbit's orientation in space. The longitude of the ascending node tells you where the orbit crosses the plane of the solar system going upward. The argument of perihelion tells you where in the orbit the object comes closest to the Sun. The true anomaly tells you where the object is in its orbit at a specific time. For the Planet 9 hypothesis, the clustering shows up in the argument of perihelion and the longitude of the ascending node. The ET-NOs tend to reach perihelion in a specific direction, and their orbital planes tend to be aligned in similar ways. Batygin and Brown's original 2016 paper identified 6 ET-NOs with well-determined orbits that showed strong clustering. Their arguments of perihelion were all within about 100 degrees of each other, clustered near 0. Their longitudes of ascending node were also grouped together. Running statistical tests, they calculated that the probability of this happening by chance was about 0.007%. That's a strong signal. But statistics can be tricky, especially with small sample sizes. 6 objects isn't many. What if those 6 happen to be the outliers, and the true population is random? That question drove the next phase of research. Astronomers searched for more ET-NOs to enlarge the sample. By 2018, the number of known ET-NOs with semi-major axes greater than 250 AU had grown to about a dozen. Some of the new discoveries fit the clustering pattern. Others didn't. The statistical significance dropped a bit, but remained intriguing. Shankman and collaborators published a paper in 2017 arguing that when you account for observational biases, the clustering might not be as significant as it appears. They ran simulations of surveys and found that biased discovery could produce apparent clustering even from a random population. Batygin and Brown responded with updated analyses. They argued that Shankman's simulations made specific assumptions about the survey biases that might not be accurate. When you account for biases differently, the clustering remains significant. They also pointed out that the clustering isn't just in one parameter, but in multiple parameters simultaneously. The ET-NOs aren't just clustered in argument of perihelion, they're also clustered in longitude of ascending node and inclination. Having multiple independent signals all pointing in the same direction strengthens the case. It's harder to explain away as bias or coincidence when several different orbital elements are aligned. One of the most compelling pieces of evidence came from a different kind of clustering. Some ET-NOs have orbits that are not just aligned, but also confined to a narrow range of inclinations. They all tilt away from the plane of the solar system in a similar direction, creating what's called pole clustering. Imagine each orbit as a disk. The pole is the direction perpendicular to that disk. If you plot the poles of the ET-NO orbits on a sphere, they should be randomly scattered. Instead, they cluster in one region. This pole clustering is independent of the perihelion clustering, providing a second line of evidence for Planet 9. To understand why Planet 9 would cause this, you have to think about how gravitational perturbations work. A distant massive planet exerts a torque on the orbits of smaller objects. Over millions of years, this torque can tilt the orbits, changing their inclination and rotating their orbital planes. If Planet 9 is in a specific orbit, it will tilt Ethnos in a specific way, creating pole clustering. Batygin simulations showed that a Planet 9 with the right mass and orbit produces both the perihelion alignment and the pole clustering. It's a two-for-one explanation that's hard to achieve with alternative models. But the dynamics are more complicated than just Planet 9 pushing Ethnos around. Neptune plays a role too. Ethnos aren't completely isolated from the known planets. Even though their perihelia are beyond Neptune, they can still interact with it through resonances or close approaches during their long orbits. Neptune's gravity can kick Ethnos into different orbits, sometimes helping Planet 9 shepherd them into alignment, sometimes disrupting the pattern. Understanding the full dynamical picture requires simulations that include both Planet 9 and Neptune, tracking the orbits of Ethnos over billions of years to see how they evolve. These simulations are computationally expensive. Each Ethno has to be integrated through its orbit, accounting for gravitational forces from the Sun, the 4 giant planets, and the hypothetical Planet 9. The simulation runs forward in time, calculating the object's position and velocity at each step. Small numerical errors can accumulate over long timescales, so the integrations have to be done carefully with high precision. Researchers run ensembles of simulations with slightly different initial conditions or different Planet 9 parameters to see which configurations best match the observed ETNOs. The results consistently show that Planet 9 with a mass of about 5 to 7 Earth masses, an orbit with a semi-major axis of 400 to 600 AU, an eccentricity of 0.2 to 0.5, and an inclination of about 15 to 25 degrees, produces Ethno distributions that look like what we observe. The simulations also predict that some Ethnos should be in high inclination orbits, tilted more than 90 degrees relative to the planets. These are called retrograde orbits because the objects orbit the Sun in the opposite direction. Remarkably, a few ETNOs with retrograde orbits have been found, matching the predictions. That's another point in favor of Planet 9. There's also the question of stability. If Planet 9 exists, has it been in its current orbit for the entire history of the solar system, or did it migrate there over time? Models of solar system formation suggest that the giant planets didn't form where they are today. Jupiter, Saturn, Uranus, and Neptune migrated inward and outward during the first few 100 million years, gravitationally interacting with each other and with the disk of leftover planetesimals. This migration scattered objects throughout the outer solar system, creating the Kuiper belt and sending comets into the Oort cloud. Planet 9 could have formed closer to the Sun, perhaps in the region where Uranus and Neptune are now, and been scattered outward by gravitational interactions with the other planets. Simulations of this scattering process show that it's possible for a planet to be ejected into a distant eccentric orbit without being thrown out of the solar system entirely. The planet needs to lose just enough energy to stay bound to the Sun, but not so much that it settles into a circular orbit close in. This is a delicate balance, but it happens in a small fraction of simulations. If Planet 9 formed in the inner part of the planetary system and was scattered outward, it would explain why it's so far away and why its orbit is so eccentric. It also means Planet 9 might have a composition similar to Uranus and Neptune, since it formed in the same region. The orbital mechanics keep pointing back to Planet 9. No matter how you slice the data, no matter which ETNOs you include or exclude, the signal persists. It's not as strong as some would like, and it's not as weak as skeptics claim. It's right in that frustrating middle ground where the evidence is tantalizing but not definitive. What astronomers need is a smoking gun, an Ethno with an orbit that can only be explained by Planet 9, or better yet, a direct detection of the planet itself. Until that happens, the debate will continue. the strange case of the tilted solar system. Here's something that doesn't get talked about enough. The entire solar system is tilted, not relative to anything outside, but relative to the Sun itself. The Sun spins on its axis, and that axis is tilted about 6 degrees compared to the average plane where the planets orbit. That might not sound like much, but it's weird. The solar system formed from a spinning disk of gas and dust. As the disk collapsed under gravity, it flattened into a pancake with the Sun at the center. The planets formed within this disk and should all orbit in the same plane as the Sun's equator. But they don't. They're tilted by 6 degrees and nobody knows why. For decades, this 6-degree tilt was a minor curiosity, the kind of thing that gets mentioned in textbooks and then forgotten. Maybe the Sun's spin axis was bumped by interactions with nearby stars when the solar system was young. Maybe the protoplanetary disk was turbulent and didn't settle into a perfectly flat configuration. There were hand-wavy explanations, but nothing concrete. Then, in 2016, researchers realized that Planet 9 could explain it. The idea works like this. If Planet 9 is in a highly inclined orbit, it exerts a gravitational torque on the rest of the solar system. Over billions of years, this torque causes the plane where the planets orbit to precess, wobbling like a spinning top. If Planet 9's orbit is tilted just right, the precession could cause the planetary plane to tilt away from the Sun's equator by exactly 6 degrees. When Batygin ran the numbers, he found that a Planet 9 with the same mass and orbit that explained the ETNOs also explained the tilt of the solar system. It was another unexpected prediction that the hypothesis got right. This is the kind of result that makes scientists sit up and pay attention. Finding one piece of evidence for Planet 9 is interesting. Finding 2 independent pieces is compelling. Having a hypothesis that explains both the ETNO clustering and the solar system's tilt starts to look less like coincidence and more like truth. It's the difference between finding a fingerprint at a crime scene and finding fingerprints, DNA, and a motive all pointing to the same suspect. But wait, there's more. In 2017, researchers discovered that Planet 9 might also explain the existence of objects with extreme inclinations. A few trans-Neptunian objects have been found with orbital tilts greater than 90 degrees, meaning they orbit the Sun in a retrograde direction opposite to the planets. These objects are incredibly hard to explain with conventional models. Neptune's gravity would normally eject them or drag them into prograde orbits aligned with the planets. They shouldn't exist, yet they do. Simulations with Planet 9 show that its gravity can flip ETNOs into retrograde orbits under certain conditions. As Planet 9 orbits the Sun, it tugs on nearby objects. Most of the time, this tug aligns the objects into the clustered prograde orbits we see. But occasionally, an object gets caught in a resonance with Planet 9 that pumps up its inclination, tilting it more and more until it flips over into a retrograde orbit. Once it's retrograde, it's stable. Planet 9 and Neptune's gravity balance each other, keeping the object locked in its unusual orbit. Without Planet 9, these retrograde ETNOs shouldn't exist. With Planet 9, they're a natural consequence of the dynamics. The list of things Planet 9 explains keeps growing: the ETNO clustering, the solar system's tilt, retrograde trans-Neptunian objects, the existence of Sedna and other extremely detached objects with perihelia far beyond Neptune. Each piece of evidence adds to the case. It's like assembling a jigsaw puzzle where Planet 9 is the missing piece that makes everything fit together. But here's the catch: we still don't have the piece. We have the shape of the hole it should fill, and we're increasingly confident about what the piece looks like, but we haven't found it yet. Skeptics point out that fitting multiple lines of evidence can be misleading. If you have enough free parameters in your model, you can fit almost any data. Planet 9's mass, orbit, and position are all adjustable parameters. Maybe the researchers are tuning the model to match the observations, and if you tuned it differently, you'd find a different solution that fits just as well. That's a fair criticism in principle, but in practice, the models are constrained by physics. Planet 9 can't be arbitrarily massive or arbitrarily far away. It has to fit within the bounds of what's possible for a planet to survive in the outer solar system for billions of years. And within those constraints, the solutions consistently point to a planet of 5 to 7 Earth masses at a few hundred AU. There's also the question of why Planet 9 would be tilted relative to the other planets. If it formed in the protoplanetary disk like Jupiter and Saturn, it should orbit in the same plane. The inclination of 15 to 25 degrees suggests something unusual happened. The most likely explanation is that Planet 9 was scattered by gravitational interactions with the other giant planets early in the solar system's history. When planets migrate and interact, they can kick each other into tilted orbits. Planet 9 might have started closer to the Sun, interacted with Neptune or Uranus, and been flung outward into an inclined orbit. This scattering process has been seen in simulations of the early solar system and is thought to be responsible for the Kuiper belt and the Oort cloud. If Planet 9 was scattered outward, it raises interesting questions about the solar system's formation. Did we start with 5 giant planets instead of 4? Some models suggest that an additional ice giant formed between Saturn and Uranus and was ejected during the period of instability when the planets were migrating. Most simulations show this 5th planet being ejected entirely into interstellar space. But in a small fraction of cases, it could be scattered into a distant bound orbit, becoming Planet 9. If that's what happened, Planet 9 is a relic from the solar system's violent youth, a survivor that holds clues to how planets form and interact. The tilted solar system remains one of the most elegant pieces of evidence for Planet 9. It's not something you'd think to look for unless you already had the hypothesis. The fact that Planet 9 explains it almost as a side effect, a bonus prediction that falls out of the math, gives the hypothesis credibility. It suggests the researchers aren't just cherry-picking data to fit their model, but have stumbled onto something real that connects disparate observations in unexpected ways. When the outer solar system gets even stranger. As if the Planet 9 hypothesis wasn't strange enough, recent discoveries have added new layers of weirdness to the outer solar system. In 2018, astronomers discovered a new dwarf planet called Goblin, officially designated 2015 TG 387. Goblin has one of the most extreme orbits ever recorded. Its perihelion is 65 AU, well beyond Neptune, and its aphelion is around 2,300 AU, taking it deep into the inner Oort cloud. One orbit takes roughly 40,000 years. Goblin never gets close enough to Neptune to be significantly affected by its gravity, making it what's called a detached object. Its orbit is tilted about 11 degrees from the ecliptic plane, and its argument of perihelion aligns with the other ETNOs that support Planet 9. What makes Goblin interesting is that it was discovered as part of a systematic survey specifically designed to test the Planet 9 hypothesis. The discoverers, Scott Shepard and Chad Trujillo, were searching regions of the sky where Planet 9's gravity would have the strongest effect. Finding Goblin exactly where the models predicted gave the hypothesis a boost. Goblin isn't just consistent with Planet 9, it's exactly the kind of object you'd expect to find if Planet 9 exists. Then there's Farfarout, discovered in 2018 and announced in 2021 after its orbit was confirmed. Farfarout is currently the most distant known object in the solar system, at about 132 AU from the Sun as of its discovery. Its orbit is highly elliptical, ranging from 27 AU at perihelion, close enough to cross Neptune's orbit, to over 175 AU at aphelion. One orbit takes about 1,000 years. Farfarout is smaller than Goblin, maybe 250 miles across, but its extreme distance made headlines when it was announced. Like Goblin, Farfarout's orbit shows hints of the clustering patterns associated with Planet 9, though its perihelion is close enough to Neptune that it's probably being influenced by both Neptune and the hypothetical Planet 9. Objects like Goblin and Farfarout are the tip of the iceberg. There are likely thousands of similar objects lurking in the outer solar system, too faint and distant to detect with current technology. Every new discovery adds a data point, refining our understanding of the trans-Neptunian region and testing the Planet 9 hypothesis. Some discoveries strengthen the case, others complicate it. The outer solar system is turning out to be far more complex and populated than anyone expected even a decade ago. One of the strangest recent findings involves objects called extreme detached objects, or EDOs. These are similar to ETNOs, but even more isolated from the planets. Their perihelia are so far out that they're barely influenced by Neptune at all. Sedna is the classic example, with a perihelion of 76 AU and an orbit that takes 11,400 years. In 2012, astronomers discovered another EDO called 2012 VP 113 with a perihelion around 80 AU. These objects are mysteries in their own right. How did they get into such detached orbits? Neptune's gravity alone can't put them there. You need something else, something that gave them a gravitational kick during the solar system's formation. One explanation is that the Sun formed in a stellar nursery alongside hundreds or thousands of other young stars. Gravitational interactions with passing stars could have perturbed objects in the outer solar system, scattering them into detached orbits. Another idea is that a rogue planet passing through the solar system billions of years ago stirred things up. Or maybe Planet 9 itself is responsible. It's gravity sculpting the orbits of these distant objects into their current configurations. Each explanation has pros and cons, and disentangling them requires more data and more sophisticated simulations. The discovery rate of trans-Neptunian objects has accelerated in recent years, thanks to improved surveys. The Dark Energy Survey, primarily designed to study galaxies and dark energy, has been used to search for distant solar system objects. Pan-STARRS and other wide-field surveys routinely discover new ETNOs. As the sample size grows, patterns become clearer or muddier, depending on your perspective. Some newly discovered ETNOs fit the clustering, others don't. The statistical significance of the clustering fluctuates as new data comes in. It's a frustrating situation for everyone involved, proponents and skeptics alike. And there's also the problem of what's called the Kuiper cliff. The Kuiper belt doesn't extend indefinitely. Observations show that the population of objects drops off sharply beyond about 50 AU. This cutoff is called the Kuiper cliff, and it's not well understood. Some models suggest that Planet 9's gravity swept out the region beyond 50 AU, scattering objects into more distant orbits or ejecting them entirely. If that's true, it would explain both the Kuiper cliff and the existence of scattered and detached objects farther out. But other models propose that the cliff is a natural result of how the protoplanetary disk evolved, with less material available at greater distances to form objects in the first place. Another puzzle involves the so-called centaurs, objects that orbit between Jupiter and Neptune with unstable orbits. Centaurs are thought to originate from the Kuiper belt or scattered disk and are gradually migrating inward due to gravitational perturbations. Eventually, they either collide with a planet, get ejected from the solar system, or become short-period comets. The existence of centaurs suggests a steady supply of objects being fed inward from the outer solar system. If Planet 9 exists, it might play a role in this process, kicking Kuiper belt objects into unstable orbits that eventually become centaurs. One of the more recent twists in the Planet 9 saga involves the orbit of Pluto itself. Pluto is in a 3-2 resonance with Neptune, which protects it from close encounters despite its orbit crossing Neptune's path. But Pluto's orbit is also tilted about 17 degrees relative to the plane of the planets. Some researchers have suggested that this tilt might be related to Planet 9's influence over billions of years. If Planet 9's gravity has been perturbing the outer solar system for the entire history of the Sun, it could have gradually tilted Pluto's orbit along with the orbits of other objects. Testing this idea requires long-term simulations that track Pluto's orbit over billions of years, accounting for the gravitational effects of all the planets, plus Planet 9. Early results are inconclusive, but they hint that Planet 9's influence might extend even to objects as close in as Pluto. The outer solar system is revealing itself to be a dynamic, complex environment where gravitational interactions play out over timescales longer than human civilization has existed. Every new discovery adds to the picture, sometimes clarifying, sometimes complicating. The hunt for Planet 9 has become as much about understanding the architecture and history of the solar system as it is about finding a single planet. Whether or not Planet 9 exists, the search has already revolutionized our knowledge of what lies beyond Neptune. The technology that could solve the mystery. Finding Planet 9 requires the right combination of telescope power, survey strategy, and data processing. The problem isn't just that Planet 9 is faint, it's that the search area is enormous and the planet is moving slowly. Traditional asteroid searches look for objects that move noticeably between images taken hours or days apart. Planet 9 would move so slowly that you'd need images separated by months or years to detect its motion. That requires a different approach, one that combines wide-field surveys with long-term monitoring and sophisticated algorithms to pick out slow-moving objects from the millions of background stars. The Vera C. Rubin Observatory is the next big hope. Scheduled to begin full operations in the mid-2020s, Rubin will conduct the Legacy Survey of Space and Time, or LSST, imaging the entire southern sky every few nights. Its 8.4-meter primary mirror and 3.2 gigapixel camera will detect objects far fainter than current surveys can reach. Every image will be compared with previous images to identify anything that has moved or changed. The data processing pipeline will automatically flag moving objects, asteroids, comets, and potentially Planet 9. Rubin's strength is its combination of depth and coverage. It will reach objects as faint as magnitude 24.5 in repeated images, significantly deeper than most other surveys. Planet 9, depending on where it is in its orbit, might be anywhere from magnitude 20 to 25. If it's at the brighter end, Rubin will spot it easily. If it's at the faint end, it will be near the detection limit, requiring multiple observations to confirm. The survey's strategy of revisiting the same fields multiple times over months and years is ideally suited for detecting slow-moving objects like Planet 9. There's also the possibility of using the James Webb Space Telescope, or JWST. Webb's infrared capabilities make it sensitive to cold objects that emit thermal radiation. Planet 9, if it has any residual heat from its formation, would glow in the infrared. JWST could detect it if someone pointed the telescope at the right patch of sky. The challenge is that JWST's field of view is tiny, less than 1/10 of a degree across. Using it to search for Planet 9 would be like looking for a needle in a haystack with a microscope. You'd need to already know roughly where Planet 9 is to make JWST observations practical. But if Rubin or another survey identifies a candidate, JWST could follow up with detailed observations to confirm the detection and characterize the planet's properties. Another tool in the arsenal is archival data. Astronomers have been imaging the sky for over a century, and all those images are stored in archives. If Planet 9 was captured in an image decades ago, it might be possible to find it by comparing old photographic plates or digital images with recent observations. The trick is that Planet 9 would look like a faint star in any single image. Only by comparing images taken years or decades apart can you see the motion. Several research groups have been mining archival data looking for Planet 9 candidates. So far, nothing definitive has turned up, but the search continues. There's also the potential for citizen science. The Planet 9 search generates massive amounts of data, far more than professional astronomers can analyze alone. Projects like Backyard Worlds, Planet 9 enlist volunteers to scan images looking for moving objects. Thousands of people have participated, examining data from NASA's WISE mission and other surveys. Citizen scientists have discovered numerous brown dwarfs and other objects, proving the approach works. If Planet 9 is in the data, there's a chance a volunteer will be the one to spot it. Advances in machine learning and artificial intelligence are also helping. Researchers are training neural networks to recognize the patterns that Planet 9 would create in survey data. A planet moving slowly across the sky leaves a faint trail when you stack images taken over time. The discovery of Neptune in 1846 was based partly on unexplained perturbations in Uranus's orbit. The same principle could apply to Planet 9, though the effect would be much smaller given the distances involved. Ground-based observatories are also stepping up their game. The Subaru telescope's Hyper-Suprime Cam has been systematically searching for Planet 9 for years. The Magellan telescopes in Chile have been used for follow-up observations of candidate objects. Large surveys like the Zwicky Transient Facility scan the northern sky nightly, and while their primary goal is finding supernovae and other transient events, they also pick up moving solar system objects. Every telescope that images the sky is potentially contributing data to the Planet 9 search, even if that's not its main purpose. The strategy moving forward involves a combination of all these approaches. Wide field surveys like Rubin will provide the discovery data. Follow-up observations with larger telescopes will confirm candidates and measure orbits. Archival searches will extend the time baseline, improving orbit determinations. Machine learning will help sift through the data deluge. Citizen scientists will provide extra eyes on hard-to-analyze images, and space-based observatories like JWST will characterize any confirmed detection. It's a multi-pronged approach that leverages the strengths of different techniques and technologies. The timeline for finding Planet 9 is uncertain. If it's bright and in a well-surveyed part of the sky, it could be found any time. Rubin's LSST might detect it within the first year of operations. On the other hand, if Planet 9 is faint or in a region of the sky that's hard to search, like near the plane of the Milky Way, where background stars are dense, it could take many more years. Some estimates suggest that if Planet 9 exists and is within the predicted range of properties, there's a good chance it will be found by the end of the 2020s. But that's not a guarantee. The solar system has a history of keeping secrets longer than anyone expects. What happens if we find it? Let's imagine the moment arrives. An astronomer or a citizen scientist spots an object moving slowly through archival images. Follow-up observations confirm it's real, not an artifact or a background star. Orbit calculations show it's distant, massive, and has the properties predicted for Planet 9. The announcement goes out. What happens next? First, there would be an explosion of scientific activity. Every telescope that can reach the object would be pointed at it. Spectroscopic observations would measure its composition, looking for signatures of water, methane, ammonia, and other molecules in its atmosphere. Infrared observations would measure its temperature and search for moons or rings. Detailed orbit determinations would refine its path and look for interactions with other objects in the outer solar system. The planet would go from a hypothetical dot on a chart to a fully characterized world. The discovery would also trigger a cascade of new questions. How did Planet 9 form? Was it born in the outer solar system, or did it migrate there from closer in? If it migrated, what does that tell us about the early solar system's dynamics? Does it have an atmosphere? And if so, what's it made of? Are there any moons orbiting it? Could it have captured any Kuiper Belt objects as moons? Is there any geological activity like cryovolcanism, or is it a frozen dead world? One of the first priorities would be naming it. The International Astronomical Union has rules for naming planets, typically drawing from mythology. Given that the existing planets are named after Roman gods, Planet 9 would likely follow suit. Possible names that have been floated include Neptune's counterparts from other mythologies, or gods associated with the underworld and distant realms. The naming process can be contentious, as evidenced by the debates over Pluto's demotion, so expect plenty of public interest and argument. From a scientific standpoint, Planet 9's discovery would reshape our understanding of solar system formation. Current models assume the solar system had 4 giant planets. If there's a 5th, it means our models are incomplete. Researchers would revisit simulations of the protoplanetary disk, planetary migration, and the NICE model, which describes how the giant planets moved to their current positions. Planet 9's existence would add a new piece to the puzzle, one that could explain anomalies in the outer solar system and provide clues about how planetary systems form in general. The discovery would also have implications for the search for planets around other stars. Super-Earths and mini-Neptunes are the most common types of exoplanets, yet the solar system doesn't have any, at least not among the known planets. If Planet 9 exists and is a super-Earth, it would fill that gap, showing that our solar system isn't as unusual as it seems. Understanding Planet 9's properties would inform models of how these planets form and evolve, helping interpret observations of exoplanets. There's also the question of whether Planet 9 could be visited by a spacecraft. At several hundred AU, it's far beyond the reach of current propulsion technology for a mission that would return data in a human lifetime. The New Horizons probe took 9.5 years to reach Pluto at 40 AU. Reaching Planet 9 at 500 AU with the same technology would take over a century. Faster propulsion methods, like nuclear or solar sails, could cut the travel time, but we're still talking decades at best. A mission to Planet 9 would require planning decades in advance, and would likely not return data until the latter half of the 21st century or beyond. Despite the challenges, there would be strong interest in sending a mission. Planet 9 would be a unique target, the only known large planet in the outer solar system that hasn't been visited. A flyby mission could return images and data that ground-based telescopes can't provide, revealing details about its surface, atmosphere, and moons. An orbiter would be even more valuable, allowing long-term study and mapping. But the cost and technical hurdles would be substantial, requiring international collaboration and new technologies. The discovery would also reignite debates about what constitutes a planet. Pluto was demoted to dwarf planet status in 2006 because it hasn't cleared its orbit of other objects. Planet 9, despite being more massive, would also share its orbital zone with other trans-Neptunian objects. Would it qualify as a planet under the IAU definition, or would the definition need to be revised? Expect plenty of heated arguments and conference sessions dedicated to planetary taxonomy. For the general public, finding Planet 9 would be a moment of excitement and wonder. It would be the first new planet discovered in the solar system since Neptune in 1846, if you don't count Pluto's brief stint as the 9th planet. News outlets would cover the story extensively, and social media would light up with speculation and celebration. Schools would update textbooks. Museums would create new exhibits. Planet 9 would enter popular culture as the mysterious new world at the edge of the solar system. There would also be speculation about what the planet looks like. Based on its mass and distance from the Sun, it would likely be a cold, dark world. If it's similar to Uranus and Neptune, it might have a thick atmosphere of hydrogen and helium with traces of methane, ammonia, and water vapor. The atmosphere would probably appear blue or blue-green due to methane absorption of red light. Cloud bands and storms might be visible, though the weak sunlight and cold temperatures would make atmospheric dynamics sluggish compared to the inner planets. The surface, if there is one beneath the atmosphere, would be frozen solid, possibly with an ocean of liquid water or ammonia buried deep beneath an icy crust. Artists' renderings of Planet 9 would proliferate, depicting it as a lonely ice giant drifting through the darkness. Some illustrations might show it with rings, like Saturn, or with a large moon, like Earth. Others might depict it from the perspective of a hypothetical spacecraft approaching through the Kuiper Belt, with icy dwarf planets in the foreground and the faint sun in the background. These images would capture the public's imagination, even if the reality is that Planet 9 is just a faint dot that requires powerful telescopes to see. What happens if we don't find it? Now let's consider the other scenario. The Vera C. Rubin Observatory completes its survey. Thousands of new trans-Neptunian objects are catalogued. The outer solar system is mapped in unprecedented detail, and Planet 9 is nowhere to be found. What then? This outcome would be almost as interesting as finding it. If Planet 9 doesn't exist, then the clustering of ETNOs needs a different explanation. Astronomers would revisit the alternative hypotheses with renewed focus. Maybe the clustering really is due to observational bias, and the expanded data set reveals that the true distribution is random. Maybe the collective gravity of many smaller objects in the Kuiper belt is responsible. Maybe there's some dynamical mechanism we haven't thought of yet that naturally produces clustering without requiring a large planet. Failing to find Planet 9 wouldn't necessarily mean it doesn't exist. It could mean it's farther away or fainter than predicted, beyond the reach of even Rubin's survey. In that case, the search would continue with next-generation telescopes. Future space-based observatories with even greater sensitivity might eventually spot it. Or it could be found serendipitously by a survey designed for a different purpose, the way many astronomical discoveries happen. The non-detection would also place tighter constraints on Planet 9's properties. If Rubin doesn't find it, we could confidently say that if it exists, it must be fainter than magnitude 25 in the regions surveyed. That would imply it's either smaller than expected, farther away, or both. These constraints would feed back into theoretical models, forcing researchers to refine their predictions or abandon the hypothesis altogether. There's also the possibility that Planet 9 exists but isn't a planet. The primordial black hole hypothesis, while exotic, would remain on the table if no planetary object is found. Detecting a primordial black hole is much harder since it doesn't emit or reflect light, but gravitational lensing or other indirect methods might eventually reveal it. Similarly, if Planet 9 is a captured rogue planet with unusual properties, it might evade detection until better surveys come online. Another possibility is that Planet 9 existed in the past, but no longer does. Maybe it was ejected from the solar system by gravitational interactions with the other planets after sculpting the ETNO orbits we see today. Dynamical simulations show that planets can be ejected, though the probability is low. If that happened, the clustering would be a relic of Planet 9's former presence, a ghost signal from a planet that's now drifting through interstellar space. Failing to find Planet 9 would also shift focus to improving our understanding of the outer solar system's dynamics. Researchers would invest more effort in modeling the Kuiper belt and scattered disk, trying to reproduce the observed ETNO distributions without invoking a large planet. They'd refine simulations of solar system formation, looking for scenarios that naturally produce the clustering. They'd study how Neptune's gravity interacts with distant objects and whether resonances or other mechanisms could mimic the Planet 9 signal. The debate would continue, probably for years. Science doesn't give up on interesting questions just because the first round of searches comes up empty. Neptune's discovery took decades of observations and calculations. Planet 9, if it exists, might require similar patience. Or it might not exist at all, and the whole episode would become a cautionary tale about how even strong circumstantial evidence can lead researchers astray. Either way, the Planet 9 hypothesis has already left its mark. It's driven surveys that have vastly expanded our catalogue of trans-Neptunian objects. It's sparked research into the dynamics of the outer solar system and the history of planetary migration. It's demonstrated the power of combining observations, simulations, and statistics to tackle complex problems. Win or lose, the search for Planet 9 has advanced our knowledge of the solar system's farthest reaches. The latest candidate that's causing controversy. And now, we get to the heart of the matter. In recent months, a new candidate for Planet 9 has emerged, and it's causing a stir. This isn't just another trans-Neptunian object, or a refined prediction based on simulations. This is an actual detection, a specific object in the sky that researchers believe could be Planet 9. Except there's a problem. Several problems, actually. The object doesn't quite fit the expected properties. Its orbit is weird in ways that don't match the models, and some astronomers are skeptical that it's real at all. The story begins with a team of researchers analyzing data from an infrared survey. They noticed an object that appeared in multiple images over several years, moving slowly across the sky. The motion was consistent with a distant solar system object, not a background star or galaxy. Initial orbit calculations suggested it was far beyond Neptune, with a semi-major axis in the range where Planet 9 is expected. The team ran more analyses, checking for artifacts and false positives. The object held up. They announced their findings in a preprint paper, claiming they might have found Planet 9. The astronomy community reacted with a mix of excitement and caution. On one hand, this was exactly the kind of discovery everyone had been waiting for. On the other hand, extraordinary claims require extraordinary evidence, and the evidence so far was incomplete. The object's orbit wasn't fully determined yet. It had only been observed over a limited arc, a small portion of its full orbit. Extrapolating that arc to a complete orbit involves uncertainties, and small errors in the observations can lead to large errors in the orbit determination. Follow-up observations were attempted, but the object was faint and in a challenging part of the sky. Some observatories couldn't confirm the detection. Others saw something in the right location, but weren't sure if it was the same object. Confusion set in. Was this a real detection or a phantom? An artifact of image processing or a background object misidentified as a solar system body? The debate spilled onto social media and into conference halls, with researchers taking sides. One of the main controversies centers on the object's brightness. Based on its distance and apparent magnitude, calculations suggested it was larger than expected for Planet 9. If the object is where the discoverers claim, it should be reflecting sunlight at a rate that implies it's either more massive than predicted or has an unusually high albedo, reflecting more light than typical icy bodies. A high albedo isn't impossible. Some icy moons in the solar system reflect a large fraction of sunlight, but it would be unexpected for a planet so far from the Sun where solar wind and radiation haven't cleaned the surface. Another issue is the orbit's inclination. The models for Planet 9 predict an inclination of 15 to 25 degrees. The candidate object's orbit, based on preliminary data, suggests an inclination closer to 30 or 35 degrees. That's not impossible, but it's outside the range most simulations favor. Some researchers argue this discrepancy is evidence the object isn't Planet 9, but something else, perhaps a large trans-Neptunian object that's unrelated to the clustering of ETNOs. Others think the orbit determination is preliminary and will converge to a more reasonable inclination once more data is collected. There's also skepticism about the detection method. Infrared surveys are powerful tools, but they're prone to certain types of false positives. Transient artifacts, cosmic rays, or image processing glitches can create the appearance of a faint object that isn't really there. The team that made the discovery claims they've ruled out these possibilities, but critics want more evidence. They want the object to be independently detected by other telescopes and confirmed through astrometric measurements that track its position over time. Until that happens, doubts will linger. Adding to the controversy is the object's magnitude variability. Some observations suggest its brightness changes slightly over time, which could indicate it's rotating and has an uneven surface that reflects more light at certain orientations. Alternatively, it could mean the observations are contaminated by background stars or other sources. Variability isn't necessarily a deal-breaker. Planets can show variations due to clouds, seasons, or rotation, but it complicates the analysis and raises questions about whether the object is being correctly identified in all the images. Proponents of the discovery argue that these issues are normal for newly detected distant objects. Orbit determination improves with more observations. Brightness measurements become more accurate as better data is collected. The controversies don't invalidate the detection. They just reflect the challenges of working at the limits of what current telescopes can do. In their view, the object is real, and the anomalies will resolve as the dataset grows. Skeptics counter that extraordinary claims require extraordinary caution. History is littered with claimed discoveries of Planet X or other distant planets that turned out to be false alarms. They point to past cases where image artifacts were mistaken for real objects, or where preliminary orbit determinations were wildly wrong. Until the candidate object is confirmed beyond doubt, skepticism is warranted. Science demands rigor, especially for something as significant as discovering a new planet. What makes this latest candidate especially intriguing is that it was found in a region of the sky that theoretical models suggested might harbor Planet 9. The discoverers weren't searching randomly. They used predictions from Batygin and Brown's simulations to guide their search, focusing on areas where Planet 9's gravity would place it based on the ETNO clustering. Finding an object in the predicted region is either a stunning vindication of the models or a coincidence that will eventually be revealed as such. The next few months will be critical. Observatories around the world are being asked to look at the candidate's location and confirm or refute its existence. If multiple independent observations confirm the object and improve its orbit determination, confidence will grow. If follow-up observations fail to detect it, or if the orbit changes dramatically with new data, the discovery will be called into question. This is how science works, through cycles of claim, scrutiny, confirmation, or refutation. There's also the tantalizing possibility that the candidate is real but isn't Planet 9. It could be a large trans-Neptunian object or dwarf planet in an unusual orbit. Finding such an object would still be valuable, adding to our catalogue of distant solar system bodies and providing more data to test the Planet 9 hypothesis. But it wouldn't be the smoking gun discovery that Planet 9 proponents are hoping for. The controversy highlights a fundamental tension in modern astronomy. On one hand, researchers want to announce discoveries quickly to stake their claim and advance knowledge. On the other hand, premature announcements can lead to confusion and damage credibility if the discovery doesn't hold up. The balance between speed and rigor is difficult to strike, especially when the stakes are high and the data is at the edge of detectability. Why this matters beyond just finding another planet. At this point, you might be wondering why anyone should care about Planet 9 beyond the cool factor of finding a new planet. The answer goes deeper than just adding another entry to the list of solar system worlds. Planet 9, if it exists, would fundamentally reshape our understanding of how planetary systems form, evolve, and stabilize. It would answer questions about the solar system's architecture that have puzzled astronomers for decades. And it would provide a natural laboratory for studying a type of planet that's common around other stars, but absent from our own planetary family. Start with the question of solar system formation. The prevailing model, called the nebula hypothesis, states that the Sun and planets formed from a collapsing cloud of gas and dust about 4.6 billion years ago. As the cloud collapsed, it flattened into a disk with the proto-Sun at the center. Within the disk, dust grains stuck together, growing into pebbles, then boulders, then planetesimals hundreds of miles across. These planetesimals continued colliding and merging, eventually forming the rocky planets in the inner solar system and the cores of the giant planets farther out. Once these cores reached a critical mass, they gravitationally captured gas from the surrounding nebula, becoming the gas giants Jupiter and Saturn, and the ice giants Uranus and Neptune. This story works well for explaining the 4 giant planets we know, but it leaves unanswered questions. Why did planet formation stop beyond Neptune? The protoplanetary disk extended well beyond 30 AU, so there should have been enough material to form more planets. One answer is that the disk was less dense at greater distances, so planetesimal growth was slower. Before objects could grow large enough to become planets, the gas in the disk dispersed, blown away by solar wind and radiation. Without gas, there was no way to form gas or ice giants, leaving only small, icy bodies that became the Kuiper Belt. Planet 9 complicates this picture. If it exists, it's a large planet beyond Neptune. How did it get there? The most plausible explanation is that it formed closer to the Sun, in the region where Uranus and Neptune are, and was then scattered outward by gravitational interactions. This scattering process is a key part of the NICE model, named after the French city where it was developed. The NICE model proposes that the giant planets didn't form in their current positions but migrated over hundreds of millions of years. Jupiter moved slightly inward. Saturn, Uranus, and Neptune moved outward. During this migration, they gravitationally kicked countless planetesimals, scattering them throughout the solar system. In some versions of the NICE model, there were originally 5 giant planets, not 4. The 5th planet, roughly the mass of Uranus or Neptune, was ejected from the solar system entirely during the chaotic migration phase. Most simulations show this 5th planet being flung into interstellar space. But in a small percentage of runs, the planet ends up in a distant, eccentric orbit, bound to the Sun, but far from the other planets. That's Planet 9. If this scenario is correct, Planet 9 is a survivor, a relic of the solar system's violent youth that holds clues to how planetary systems rearrange themselves after formation. Discovering Planet 9 would confirm this aspect of the NICE model and validate the idea that planetary systems are dynamic, not static. It would show that the configuration we see today isn't the configuration that existed when the planets first formed. This has implications for exoplanetary systems. Many exoplanets orbit close to their stars in configurations that couldn't have formed in place. They must have migrated inward after forming farther out. Understanding how and why planets migrate helps explain the diversity of exoplanetary systems observed by missions like Kepler and TESS. Planet 9 would also provide insight into the formation of super-Earths and mini-Neptunes. These planets, with masses between Earth and Neptune, are the most common type found around other stars. Surveys suggest that the majority of Sun-like stars host at least one super-Earth or mini-Neptune. Yet our solar system doesn't have any, at least not among the known planets. This absence is puzzling. Are we unusual, or is there a selection effect at play? Planet 9, if it's a super-Earth or mini-Neptune, would fill that gap and show that our solar system isn't as different from others as it appears. Studying Planet 9's composition would be invaluable. Is it an ice giant like Uranus and Neptune, dominated by water, methane, and ammonia ices with a rocky core? Or is it something different? A rocky super-Earth with a thick hydrogen and helium atmosphere? The answer depends on where and how it formed. If it formed in the outer solar system from ices and rocks, it would be an ice giant. If it formed closer in and was scattered outward, it might have a different composition. Spectroscopic observations could reveal the planet's atmospheric composition, providing clues to its origin. There's also the question of moons. Nearly every planet in the solar system has moons. Jupiter has dozens, some as large as planets themselves. Saturn's moon Titan is bigger than Mercury. Neptune's moon Triton orbits in the opposite direction from Neptune's rotation, suggesting it was captured from the Kuiper Belt. If Planet 9 has moons, they would be worlds in their own right, potentially with their own geology and atmospheres. Discovering moons around Planet 9 would open up new targets for study, and possibly even future missions. The existence of Planet 9 would also shed light on the Oort cloud, the vast spherical shell of icy bodies surrounding the solar system at distances up to 100,000 AU. The Oort cloud is thought to be the source of long-period comets, objects that plunge into the inner solar system on orbits taking thousands or millions of years. How did the Oort cloud form? The leading theory is that planetesimals were scattered outward by the giant planets during the solar system's early history. Most were ejected into interstellar space, but some ended up in distant-bound orbits, forming the Oort cloud. Planet 9's gravity could have contributed to this scattering, shaping the structure and population of the Oort cloud in ways we don't yet understand. There's also a cultural and philosophical dimension to Planet 9. Humanity has always looked to the night sky with wonder, seeking to understand our place in the cosmos. Discovering a new planet in our own solar system would remind us that even our cosmic backyard holds mysteries. It would be a humbling experience, showing that despite centuries of astronomical progress, we still don't have a complete inventory of our own planetary system. At the same time, it would be a triumph of human ingenuity, demonstrating the power of mathematics, observation, and simulation to predict and discover hidden worlds. For educators and science communicators, Planet 9 would be a gift. It's the kind of story that captures imaginations, a cosmic mystery with real stakes and real science. Students learning about gravity and orbital mechanics could study how Planet 9's gravity shapes the outer solar system. Those interested in data science could explore how machine learning helps search for distant planets. Aspiring astronomers could follow the search in real time, watching as new data comes in and the picture slowly clarifies. Planet 9 would be a living, breathing example of science in action, messy and uncertain, but ultimately driven by evidence and reason. The broader impact extends to funding and public support for astronomy. Major discoveries generate public interest, which in turn supports continued investment in telescopes, missions, and research. Finding Planet 9 would justify the resources spent on surveys like Rubin and would make a strong case for future projects. It would show that even in an era when exoplanet discoveries are routine, our own solar system still has surprises left. That sense of wonder and discovery is vital for maintaining momentum in space exploration and planetary science. Finally, there's the possibility that studying Planet 9 could have unexpected applications. History is full of examples where fundamental research, pursued purely for knowledge, later led to practical technologies. Understanding orbital mechanics led to GPS satellites. Studying black holes informed data compression algorithms. We can't predict what insights might come from studying Planet 9, but experience suggests that pushing the boundaries of knowledge pays dividends in unexpected ways. At the very least, Planet 9 would be a testbed for techniques and technologies that could be applied elsewhere, from image processing algorithms to spacecraft navigation to planetary atmosphere modeling. So yes, Planet 9 matters. It matters scientifically, culturally, and practically. Whether it exists or not, the search for it has already expanded our knowledge and sharpened our tools. If it's found, it will be a landmark discovery, one that future generations will study and celebrate. If it's not found, the effort will still have been worthwhile, teaching us about the outer solar system and refining our methods for the next great mystery. Either way, the story of Planet 9 is a testament to human curiosity and our drive to explore the unknown. The objects that refuse to cooperate with our theories. If the outer solar system were a crime scene, the extreme trans-Neptunian objects would be the witnesses giving contradictory testimony. Some of them line up perfectly with what Planet 9 theory predicts. Others seem to deliberately contradict it, and a few are so bizarre that they don't fit any existing framework at all. Take 2015 BP 519 for example. This object was discovered in 2014, but its orbit wasn't confirmed until 2018. What makes it interesting is its extreme inclination, tilted about 54 degrees relative to the plane of the solar system. That's far more than most ETNOs, and it orbits the Sun in a nearly perpendicular orientation to the planets. When BP 519's orbit was first published, some researchers saw it as evidence against Planet 9. How could a hypothetical planet on a 15 to 25 degree inclined orbit produce an ETNO tilted at 54 degrees? It seemed impossible. But then, Batygin and his team ran new simulations specifically looking at high inclination objects. They found that Planet 9's gravity, combined with Neptune's, could indeed produce objects like BP 519 through a complex series of gravitational kicks over millions of years. The object would start in a more normal orbit, get perturbed by Neptune, then interact with Planet 9 in a resonance that pumps up its inclination dramatically. It's a rare outcome, but it happens in a small percentage of simulation runs. Critics weren't entirely convinced. They pointed out that you can tune a model to fit any observation if you allow enough complexity. The simulations that produced BP 519 analogues required very specific initial conditions and finely tuned interactions. Was this evidence for Planet 9, or evidence that the models had become too flexible, capable of explaining anything and therefore explaining nothing? It's a valid concern. In science, a theory that can explain every possible observation isn't a theory at all. It's just curve fitting. Then there's 2013 SY99, another oddball discovered during surveys of the outer solar system. Its orbit has a semi-major axis around 730 AU and an eccentricity of about 0.92, meaning it swings from 60 AU at perihelion out to nearly 1,400 AU at aphelion. The orbital period is roughly 20,000 years. What makes SY99 weird is that its argument of perihelion is almost exactly opposite to the clustering direction seen in other ET nodes. If most ET nodes have their perihelion near 0 degrees, SY99 has its near 180 degrees. It's anti-aligned, pointing in the exact opposite direction. Some researchers saw this as a problem for Planet 9. If Planet 9's gravity shepherds ET-nodes into aligned orbits, why is SY99 anti-aligned? Shouldn't Planet 9 affect all ET-nodes the same way? Actually, no. Batygin's simulations showed that Planet 9 can produce both aligned and anti-aligned populations, depending on how objects interact with it. Objects that are close to resonance with Planet 9 get captured into aligned orbits. Objects that aren't in resonance can be scattered into anti-aligned orbits. The existence of anti-aligned ET nodes isn't a bug in the theory, it's a feature. In fact, the models predict there should be a smaller population of anti-aligned objects, and that's what we see. But the problem is sample size. With only a couple dozen well-characterized ETNOs, it's hard to say whether the distribution matches predictions or not. Every new discovery has the potential to strengthen or weaken the case. If future surveys find lots more anti-aligned objects, it could mean the models are right. If they find very few, it could mean the alignment is less significant than it appears. The data is frustratingly ambiguous, hovering in that zone where both proponents and skeptics can point to the same numbers and draw different conclusions. Another interesting case is 2014 SR 349, an ETNO with a semi-major axis around 300 AU. What makes it notable is that it seems to be in a near resonance with the hypothetical Planet 9. If Planet 9 is where the models predict, SR 349 orbits the Sun roughly 3 times for every one Planet 9 orbit. Resonances are stable configurations that can last billions of years once established. Finding an object in resonance with Planet 9 is compelling evidence that Planet 9 exists, because resonances don't happen by accident. They require a massive perturber to lock objects into those specific orbital relationships. But there's a catch. To confirm a resonance, you need to know both objects' orbits precisely. We have a good orbit for SR 349 based on multiple observations over several years. But we don't have Planet 9's orbit, only predictions. The resonance is inferred by assuming Planet 9 is where the models say it should be. If Planet 9 turns out to be in a slightly different orbit or doesn't exist at all, then SR 349 isn't in resonance with anything, and the whole argument falls apart. It's circular reasoning unless Planet 9 is actually found and its orbit confirmed. The same issue applies to several other ETNOs that appear to be in resonances with the hypothetical Planet 9. Objects like 2015 KG 163, 2007 TG 422, and others have orbital periods that seem to be simple ratios of Planet 9's predicted period. On paper, it looks like smoking gun evidence. In practice, it's more ambiguous because the resonances depend on assumptions about where Planet 9 is. If those assumptions are wrong, the resonances disappear. What makes the situation even more complicated is that some ETNOs don't show any clustering at all. Their orbits are randomly oriented with arguments of perihelion scattered all over the place. Are these objects part of a different population that Planet 9 doesn't affect? Or are they proof that the clustering in other ETNOs is just noise? Researchers have proposed that there might be multiple populations of ETNOs with different dynamical histories. Some were scattered by Neptune early in the solar system's history and now have random orbits. Others have been influenced by Planet 9 and show clustering. The challenge is distinguishing between these populations when the sample size is small and the observational biases are large. One of the most frustrating aspects of the ETNO data is that many of the objects are observed for only a small fraction of their orbits. An object with a 10,000-year orbital period might be observed for 5 or 10 years, giving us less than 0.1% of its full orbit. Extrapolating from such a small arc to the full orbit introduces uncertainties. Small errors in position measurements propagate into large uncertainties in orbital parameters like eccentricity and semi-major axis. An object that appears to be an ETNO based on limited data might turn out to have a very different orbit once more observations are made. There have been cases where preliminary orbit determinations were wildly off. An object initially thought to be at 200 AU turned out to be at 80 AU after more data came in. Another object, thought to have a highly eccentric orbit, was later found to be on a nearly circular path. These corrections happen because orbit fitting is a statistical process. The more data you have, the better the fit. But early on, with limited observations, there's a lot of wiggle room in the solutions. This uncertainty makes it hard to assess how many true ETNOs exist and whether their clustering is real. To address this, astronomers are pushing for long-term monitoring programs that track ETNOs over decades. The longer the baseline of observations, the more accurate the orbit determination. But this requires patience and sustained funding. Telescopes need to revisit the same objects year after year, taking time away from other projects. It's not glamorous work, but it's essential for building a reliable catalogue of outer solar system objects. Only with that catalogue can we definitively test the Planet 9 hypothesis. In the meantime, every new ETNO discovery is scrutinized. Does it fit the clustering? Is it aligned or anti-aligned? What's its inclination? How certain is the orbit? Each object is a new data point, and astronomers update their statistical analyses accordingly. The significance of the clustering has fluctuated over the years as new objects are added. Sometimes it goes up, sometimes it goes down. The trend overall has been toward clustering remaining significant, but not overwhelmingly so. It's the kind of situation that keeps the debate alive and ensures that Planet 9 remains one of the most hotly contested topics in planetary science. The role of computer simulations in hunting ghosts. Modern astronomy relies heavily on computer simulations, and nowhere is that more true than in the search for Planet 9. You can't run experiments on planetary orbits. You can't put the solar system in a lab and tweak variables to see what happens. The only way to test ideas about Planet 9 is to build computer models that simulate millions of years of gravitational interactions and see if the outcomes match observations. These simulations are remarkably complex, involving physics, numerical methods, and massive computational power. At the heart of every simulation is Newton's law of universal gravitation, or in some cases, Einstein's general relativity for higher precision. The basic idea is simple. Every object in the solar system exerts a gravitational force on every other object. The force depends on the masses of the objects and the distance between them. By calculating all these forces at each moment in time, you can predict how objects move. In practice, this is fiendishly complicated because there are many objects, and their positions are constantly changing. The numerical method used is called n-body integration. You start with the current positions and velocities of all the objects you want to track: the Sun, the planets, and any asteroids or trans-Neptunian objects you're interested in. Then you calculate the gravitational forces acting on each object from all the others. Using these forces, you compute how each object's velocity changes over a small time step. typically a few days or weeks. Then you update each object's position based on its new velocity. Repeat this process millions of times, stepping forward through simulated time, and you get a picture of how the system evolves. For Planet 9 simulations, researchers typically include the Sun, the 4 giant planets, and a population of test particles representing ethnos. Planet 9 is added as another massive body with a specified orbit. The simulation runs forward for millions or even billions of years, tracking how the test particles' orbits change due to gravitational interactions. At the end, you examine the distribution of orbits and see if it matches the observed ethnos. If it does, the Planet 9 model is consistent with the data. If it doesn't, the model needs adjustment. Running these simulations requires serious computational resources. A single simulation with thousands of test particles can take days or weeks on a powerful computer. Researchers often run ensembles of simulations with slightly different parameters, exploring a range of possible Planet 9 masses, orbits, and initial conditions. Each ensemble might include hundreds of individual runs. The goal is to map out the parameter space and identify which regions produce ETNO distributions that match observations. One challenge is stability. The solar system has existed for 4.6 billion years, so any valid model has to produce orbits that remain stable over that timescale. If a simulation shows Planet 9 crashing into Neptune or being ejected from the solar system after a few million years, that model is ruled out. Testing stability requires running simulations for billions of simulated years, which is computationally expensive. Researchers use tricks to speed things up, like adaptive time steps that take larger steps when objects are far apart and smaller steps during close encounters. But it's still a resource-intensive process. Another challenge is the chaotic nature of orbital dynamics. The solar system is a chaotic system in the mathematical sense, meaning small changes in initial conditions can lead to large differences in outcomes over time. Two simulations that start with nearly identical setups can diverge dramatically after millions of years. This sensitivity to initial conditions makes it hard to draw definitive conclusions from simulations. You can show that certain outcomes are possible, but you can't prove they're the only possibilities or even the most likely ones. To deal with chaos, researchers run statistical analyses on ensembles of simulations. Instead of asking whether a single simulation matches the data, they ask what fraction of simulations produce outcomes consistent with observations. If 50% of simulations with a particular Planet 9 model produce clustered ETNOs, that's a strong signal. If only 5% do, the model is less compelling. This statistical approach helps quantify uncertainty and gives a more honest picture of what the models can and can't tell us. Simulations have also been used to make predictions that can be tested observationally. For example, Batygin's team predicted that if Planet 9 exists, there should be a population of high-inclination ETNOs with tilts greater than 40 degrees. These objects would be rare, but they should exist. When BP 519 was discovered with a 54-degree inclination, it was seen as confirmation of that prediction. Similarly, simulations predicted that some ETNOs should be in retrograde orbits, and several such objects have been found. Each confirmed prediction strengthens the case for Planet 9. But simulations have limits. They're only as good as the physics and assumptions that go into them. If Planet 9 interacts with the solar system in ways we haven't thought of, the simulations might miss it. If there are additional unmodeled effects like the influence of passing stars or the collective gravity of the Kuiper belt, the results could be skewed. Simulations are tools for exploring possibilities, not crystal balls, that reveal truth. They guide research and suggest where to look, but they can't replace actual observations. There's also the question of computational bias. Researchers naturally focus on simulations that produce interesting results. A simulation that shows no clustering or no Planet 9 effect might be dismissed as uninteresting and not pursued further. This can create a bias where the published literature overrepresents positive results and underrepresents negative ones. To counter this, some teams have made efforts to publish null results, showing simulations that don't support Planet 9 to provide a more balanced view. Despite these challenges, computer simulations remain indispensable. They allow researchers to test ideas that would be impossible to test any other way. They provide a framework for interpreting observations and making predictions, and they've been remarkably successful at explaining complex phenomena in the outer solar system. As computational power continues to grow, simulations will become even more detailed and accurate, incorporating more objects, longer timescales, and better physics. The hunt for Planet 9 is as much a computational endeavor as an observational one, and advances in both areas are needed to solve the mystery. The history of planets that weren't there. Planet 9 isn't the first time astronomers have predicted a planet beyond the known ones. The history of such predictions is a mix of triumphs and embarrassments, and it's worth understanding that history to put the current search in context. The most famous success story is the discovery of Neptune. In the early 1800s, astronomers noticed that Uranus's orbit didn't quite match predictions based on Newton's laws. Something was perturbing it. In the 1840s, two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated where an unknown planet would need to be to explain Uranus's motion. Le Verrier sent his predictions to Johann Galle at the Berlin Observatory, and within hours of starting the search, Galle found Neptune almost exactly where Le Verrier said it would be. It was a stunning vindication of Newtonian mechanics and the power of mathematical prediction. Emboldened by this success, astronomers started looking for more planets. Soon after Neptune's discovery, there were claims that its orbit also showed discrepancies, suggesting yet another planet farther out. This hypothetical planet was called Planet X, and the search for it consumed astronomers for decades. Percival Lowell, the wealthy astronomer who built Lowell Observatory in Arizona, became obsessed with finding Planet X. He spent years calculating where it should be and scanning the sky with telescopes. Lowell died in 1916 without finding it, but his observatory continued the search. In 1930, Clyde Tombaugh, a young astronomer at Lowell Observatory, discovered Pluto. It was in roughly the region where Lowell had predicted Planet X should be, and for a while, Pluto was hailed as the long-sought ninth planet. There was just one problem. Pluto was far too small to account for the supposed perturbations in Neptune's orbit. Its mass was estimated at a fraction of Earth's, not nearly enough to gravitationally tug on Neptune in any significant way. Over the following decades, as better data on Neptune's orbit accumulated, it became clear that the perturbations Lowell thought he saw were actually errors in the observations. There was no discrepancy to explain. Planet X didn't exist, at least not the Planet X that Lowell envisioned. Pluto's discovery was partly luck and partly the result of a systematic search, but it wasn't the massive planet that Lowell was looking for. When the Voyager 2 spacecraft flew by Neptune in 1989, it measured the planet's mass more accurately than ever before. Using that data, astronomers recalculated Neptune's orbit and found it matched observations perfectly. No additional planet was needed. The search for Planet X was officially over, a cautionary tale about how observational errors can lead scientists on wild goose chases lasting decades. The lesson from the Planet X saga is that extraordinary claims require extraordinary evidence. Just because orbits seem perturbed doesn't mean there's a hidden planet. Errors in measurements, unmodeled effects, or statistical flukes can create the appearance of discrepancies that aren't real. This is why the Planet 9 hypothesis faces such scrutiny. Astronomers remember Lowell's obsession and don't want to repeat his mistake. They demand rigorous statistical analyses, consideration of observational biases, and independent confirmation before accepting that Planet 9 exists. But there's another lesson too. Sometimes the predictions are right, even if for the wrong reasons. Pluto was discovered during a search for a planet that didn't exist, yet Pluto itself is real. Neptune was found based on perturbations that were correctly measured and calculated. The method works when applied carefully with good data. The Planet 9 hypothesis is grounded in modern observations and sophisticated simulations, not century-old orbital calculations done by hand. The tools are better, the data is better, and the theoretical framework is more robust. That doesn't guarantee Planet 9 exists, but it means the search is on firmer ground than Lowell's ever was. There have been other false alarms in recent decades too. In the 1980s and 1990s, several astronomers claimed to have detected planet-sized bodies in the outer solar system based on infrared observations or dynamical effects. None of these claims held up to scrutiny. One famous case involved the Infrared Astronomical Satellite, or IRAS, which detected several mysterious infrared sources that some speculated could be a brown dwarf or large planet orbiting the Sun. Follow-up observations showed they were distant galaxies, not solar system objects. Another case involved claims that comets' orbits showed perturbations indicating a large planet in the Oort cloud. Those claims were eventually debunked as well. These false alarms have made astronomers cautious, perhaps overly so. There's a bias towards skepticism when it comes to claims of new planets, especially in the outer solar system, where observations are difficult and errors are easy. That skepticism is healthy in principle, but it can also slow progress if it becomes too rigid. The key is balancing openness to new ideas with rigorous standards of evidence. Planet 9 proponents argue they've met those standards. Skeptics disagree. The debate continues, as it should, until definitive evidence one way or the other settles the matter. It's also worth noting that the history of astronomy is full of surprises. Uranus was discovered by accident in 1781 when William Herschel thought he'd found a comet. The asteroid belt was discovered in the early 1800s when astronomers were searching for a predicted planet between Mars and Jupiter. Pluto was found during a search for something else entirely. The universe has a habit of revealing things when we're not expecting them, in ways we didn't anticipate. Planet 9 might be found by a survey designed to study galaxies or dark energy, not by a dedicated Planet 9 search. Serendipity plays a bigger role in astronomy than most people realize. The history also shows that planetary science progresses in fits and starts. Long periods of incremental progress are punctuated by sudden breakthroughs that reshape our understanding. The discovery of exoplanets in the 1990s was one such breakthrough. The realization that planetary migration is common was another. If Planet 9 is found, it will be the next breakthrough, opening new avenues of research and raising new questions. If it's not found, that too will be significant, forcing theorists to rethink their models and observers to refine their techniques. Either way, the field moves forward. Understanding this history puts the Planet 9 search in perspective. It's not just about finding one planet. It's about continuing a centuries-long quest to map the solar system and understand its structure. Every generation of astronomers has pushed the boundaries a little farther, discovering new worlds and revealing new complexities. Planet 9 is the latest chapter in that story, and whether it ends in triumph or disappointment, it's a chapter worth writing. The strange connection between Planet 9 and comets. One of the more unexpected predictions from Planet 9 models involves comets. Long-period comets, the kind that take centuries or millennia to orbit the Sun, are thought to come from the Oort cloud, a vast reservoir of icy bodies surrounding the solar system at distances up to 100,000 AU. The Oort cloud is so far away that it's barely bound to the Sun's gravity. Passing stars and galactic tides can perturb objects in the Oort cloud, sending them plunging toward the inner solar system, where they become visible as comets. Here's where Planet 9 comes in. If it exists, its gravity would affect not just ET-NOs, but also objects in the inner Oort cloud, the region between about 1,000 and 10,000 AU. Simulations show that Planet 9 could stir up this population, sending more comets toward the inner solar system than would otherwise be expected. Some researchers have looked at the statistics of long-period comet orbits to see if there's a Planet 9 signature. The results are intriguing but not definitive. One study found that long-period comets coming from a certain direction in the sky are more common than comets from other directions. This asymmetry could be explained by Planet Nine's gravity, preferentially deflecting comets into the inner solar system when they pass near it. If Planet 9 is in a specific part of its orbit, it would create a directional bias in the comet population. The data hints at this pattern, but the statistics are noisy because long-period comets are rare and their orbits are hard to measure accurately. Another connection involves the so-called sun-grazing comets, objects that pass extremely close to the Sun, sometimes within a few solar radii. These comets are thought to be fragments of larger bodies that broke apart due to tidal forces or collisions. Some models suggest that Planet 9's gravity could perturb objects in the inner Oort cloud, sending them into orbits that bring them very close to the Sun. If true, there should be a correlation between the population of sun grazers and the properties of Planet 9. Observational tests of this idea are ongoing. There's also the question of cometary reservoirs. The solar system has two main sources of comets: the Kuiper belt, which supplies short-period comets with orbits less than 200 years, and the Oort cloud, which supplies long-period comets. Planet 9's gravity could create a third reservoir, a population of objects in intermediate orbits that occasionally get perturbed into the inner solar system. This reservoir would be located in the region where Planet 9 orbits, between about 200 and 1000 AU. Detecting and characterizing this population would provide strong evidence for Planet 9. Comets are notoriously difficult to study because they're faint until they get close to the Sun, and by then they're active, surrounded by gas and dust that obscures the nucleus. Measuring a comet's orbit requires tracking it over months or years as it moves through the solar system. For long-period comets that won't return for centuries, a single apparition is all we get. That makes it hard to build up a large statistical sample with well-determined orbits. Despite these challenges, cometary studies offer another line of evidence that can test the Planet 9 hypothesis. One of the more speculative ideas is that Planet 9 could be responsible for periodic comet showers in Earth's history. The fossil record shows several mass extinction events that might be linked to comet or asteroid impacts. If Planet 9's orbit precesses or oscillates over millions of years, it could periodically disturb the Oort cloud, sending waves of comets toward the inner solar system. These comet showers would increase the impact rate on Earth, potentially causing extinctions. The idea is controversial and far from proven, but it's an example of how Planet 9 could have implications beyond just orbital dynamics. There's also interest in studying individual comets that might have been affected by Planet 9. One example is Comet Bernardinelli-Bernstein, discovered in 2021 and notable for being one of the largest comets ever found, with a nucleus estimated at over 100 kilometers across. Its orbit has a perihelion around 11 AU and an aphelion over 40,000 AU, taking it deep into the inner Oort cloud. Some researchers have speculated that its orbit might show signs of Planet 9's influence, though the data so far is inconclusive. As more large comets are discovered, each one becomes a potential test case for Planet 9 models. The connection between Planet 9 and comets highlights how interconnected the solar system is. A planet in the outer reaches can influence objects thousands of AU away through gravitational perturbations that accumulate over millions of years. These effects are subtle and hard to detect, but they're real, and they provide another way to search for Planet 9 indirectly. If the planet can't be seen with telescopes, maybe its influence on comets will give it away. The debate over what counts as evidence. At the heart of the Planet 9 controversy lies a deceptively simple philosophical question. What counts as sufficient evidence to claim a planet exists? In classical astronomy, the answer was clear. You pointed a telescope at the sky, saw a faint dot that moved relative to the background stars, tracked that motion over time, confirmed it orbited the Sun, and declared a discovery. That's how Uranus was recognized in the late 18th century, how Neptune was revealed through its gravitational fingerprints, and how Pluto was identified through painstaking photographic comparisons. direct detection has always been the gold standard. But the search for Planet 9 has turned that simple idea into something far more complicated. For nearly a decade, researchers have accumulated indirect clues, patterns in orbits, statistical anomalies, unusual objects on strange trajectories. These clues are compelling to some and unconvincing to others, raising the question, in the absence of direct detection, how much evidence is enough? For proponents of Planet 9, the case seems increasingly persuasive. The clustering of extreme trans-Neptunian objects, ETINOs, was the first hint, a pattern that appeared too neat and too consistent to arise by chance. Statistical analyses suggested that the odds of such clustering emerging randomly were very low. Simulations demonstrated that a distant planet with a specific mass and orbit could shepherd these objects into the observed configurations. The hypothesis also made predictions, some of which appeared to come true, such as the discovery of high-inclination objects and the identification of ETINOs with retrograde orbits. Add to that the tilt of the solar system's orbital plane, the puzzling motions of distant objects like Sedna, and even potential connections to long-period comets, and the entire web of evidence begins to point in one direction. None of these clues alone is conclusive, but together they create a coherent framework that seems to demand an explanation. Skeptics, however, are unconvinced. They argue that without direct detection, the entire case remains speculative. The clustering could be the result of observational bias. After all, telescopes survey some regions of the sky more thoroughly than others. Simulations can be tuned to fit the data, and predictions that appear correct might be coincidental or shaped by confirmation bias. Skeptics point to the long history of proposed missing planets that turned out to be illusions. Throughout the 19th century, astronomers speculated about intramercurial planets, missing giant worlds, and gravitational anomalies, many of which vanished once observational techniques improved. To skeptics, Planet 9 is just another chapter in that pattern. They argue that extraordinary claims require extraordinary evidence, and until a telescope captures the planet itself, everything remains hypothetical. This disagreement reflects a broader tension within the scientific process: how to balance openness to bold new ideas with caution toward unproven claims. Too much openness, skeptics warn, leads to chasing phantom phenomena and misallocating resources. Too much skepticism, proponents counter, risks missing real discoveries or dismissing legitimate anomalies. Science is built to navigate this balance through peer review, replication, and the gradual accumulation of evidence. But during an ongoing debate, before the mystery is resolved, the process can feel messy and ambiguous. One helpful way to conceptualize the Planet 9 debate is through Bayesian reasoning, an approach that updates beliefs based on new information. Imagine starting with a prior probability for the existence of a distant planet. Maybe your prior is low because the outer solar system has been surveyed extensively. Or maybe it's high because planetary formation models predict the possibility of ejected or distant planets. As new evidence appears, you update that probability. The ETINO clustering raises it. The failure to detect the planet in certain regions lowers it. The discovery of unusual objects with steep inclinations raises it again. Over time, these updates nudge your belief toward a conclusion. Different astronomers have different priors and weigh evidence differently, which naturally leads to disagreement. A researcher skeptical of poorly constrained datasets might place little weight on clustering evidence. Another who trusts dynamical simulations might find the case persuasive. Because priors are shaped by experience, intuition, and an understanding of the field, there is no single objective way to set them. The scientific goal, however, is to gather enough data that everyone's updated beliefs converge regardless of where they started. Planet 9 has not yet reached that convergence. The debate also hinges on what counts as a legitimate prediction. Proponents argue that the Planet 9 hypothesis forecasted the existence of certain classes of objects with extreme inclinations and unusual orbits, and subsequent discoveries matched those expectations. Skeptics counter that these predictions were made after similar objects were already known, turning them into postdictions rather than genuine forecasts. A true prediction, they argue, would specify where the planet should appear in the sky, or what exact properties a yet undiscovered object should have. The distinction matters because scientific predictions gain strength when they are made before relevant evidence is known. The line between prediction and postdiction is subtle, and the two sides frequently argue past each other, interpreting the same events differently. Reproducibility further complicates the issue. In laboratory sciences, reproducibility means repeating an experiment under controlled conditions. In astronomy, you cannot rerun the universe, but you can analyze data independently or conduct new surveys. Multiple teams have examined the ET-NO dataset with mixed results. Some confirm the clustering, others argue that the signal weakens when observational biases are accounted for. Survey limitations, incomplete sky coverage, and small sample sizes contribute to the uncertainty. Each new study adds nuance but rarely settles the matter. Instead, the back and forth creates a dynamic conversation, with the evidence evolving but not yet reaching consensus. Public communication adds another layer to the tension. When researchers publish a paper suggesting strong evidence for Planet 9, media outlets often simplify the results. Headlines declare the planet real, almost discovered, or on the verge of detection. The actual scientific content is usually far more tentative, full of probabilities and caveats. When follow-up studies challenge earlier claims, the public may interpret the shift as confusion, rather than the normal progression of scientific refinement. Communicating uncertainty without undermining public trust is a delicate challenge. Scientists must avoid exaggeration while still conveying the excitement and significance of the search. Resources and funding also shape the debate. Searching for Planet 9 requires time on some of the world's largest telescopes, along with significant computational power for simulations and orbit modeling. Funding agencies and observatories must decide whether the search is worth the investment. Proponents argue that the potential payoff is enormous. The discovery of a major planet would be one of the defining astronomical achievements of the century. Skeptics argue that the probability of success is too low to justify diverting resources from projects with more certain outcomes. These decisions are influenced not only by scientific merit, but also by institutional priorities, competing proposals, and long-term research goals. As a result, the search for Planet 9 becomes not just a scientific question, but a strategic one. Another dimension of the debate involves the psychology of scientific communities. Bold hypotheses naturally attract attention. They inspire enthusiasm, spark discussions at conferences, and encourage new lines of research. But they can also provoke pushback, especially when evidence is ambiguous. Some researchers worry that Planet 9 has become too popular too quickly, overshadowing alternative explanations. Others worry that skepticism has become reflexive, dismissing interesting anomalies prematurely. These interpersonal and cultural dynamics shape how ideas are received and debated, even if they rarely appear in published papers. Despite the disagreements, the scientific process continues to move forward. New surveys are underway, new ET-NOs are being discovered, and new simulations are refining predictions. The search for Planet 9 has already led to improvements in observational strategies, better models of the outer solar system, and a deeper understanding of the biases that affect distant object detection. Even if Planet 9 does not exist, the research has enriched our understanding of the solar system's architecture. The debate will be resolved not by philosophy or argument, but by evidence. If a telescope finally captures a faint moving point of light matching Planet 9's predicted properties, the controversy will collapse. The skeptics will accept the discovery, the proponents will be vindicated, and the solar system will gain a new member. If extensive surveys fail to find the planet in all plausible regions of the sky, the hypothesis will lose credibility, and researchers will seek alternative explanations for the ET-NO clustering. Until one of those outcomes arrives, the uncertainty will remain. But that uncertainty is not a flaw in science. It is a feature. It reflects the process of exploring the unknown, gathering clues, debating interpretations, and slowly inching toward the truth. The cultural fascination with hidden worlds. There's something deeply compelling about the idea of a hidden planet lurking at the edge of the solar system. It taps into a primal human curiosity about the unknown and the thrill of discovery. For all of human history, the night sky has been a canvas for imagination, myth, and speculation. Ancient civilizations tracked the motions of the visible planets, built calendars around them, and told stories about gods who used those worlds as thrones or battlegrounds. When telescopes entered the scene, the universe expanded almost overnight. The discovery of Uranus in 1781 was a seismic moment, proof that the solar system was larger than anyone realized. Neptune followed in 1846, discovered not by chance but by prediction, a triumph that made astronomers believe that mathematics itself could unveil new worlds. Pluto's discovery in 1930 added another chapter to the ongoing narrative of hidden objects slowly coming into view. Each of these discoveries reinforced the idea that the solar system is not a static, fully mapped place, but an unfolding frontier. Planet 9 fits neatly into this tradition of expanding horizons. It's big enough to matter, possibly several times the mass of Earth, yet distant enough to have avoided the sweeping surveys that transformed planetary astronomy in the 20th century. It's the perfect mix of plausible and mysterious, a world on the edge of detectability. In the public imagination, that makes it irresistible. The idea that our familiar solar system might still contain a major planet we haven't seen yet feels like a callback to the great age of discovery, when new continents, new stars, and new species were constantly being revealed. In a time when many scientific fields feel data-driven and incremental, the search for Planet 9 feels adventurous. Part of the fascination comes from the surprise factor. We live in an era of spacecraft at Jupiter, rovers on Mars, and telescopes that can spot planets around distant stars. How, people wonder, could we miss a massive planet in our own backyard? The rational explanation is straightforward. The outer solar system is unimaginably vast, and objects hundreds of astronomical units away reflect almost no sunlight. A world the size of Earth could easily be hiding in the darkness, detectable only with painstaking surveys and sensitive instruments. But emotionally, the idea hits differently. It feels like a reminder that our grip on the universe is still tenuous. No matter how advanced our technology becomes, space remains full of surprises. The media amplifies this sense of mystery. Headlines often swing between caution and sensationalism. Articles appear with titles like "Astronomers Closing In on Elusive Planet 9" or "Have Scientists Found a New Planet Beyond Neptune?" The actual papers behind these stories are usually more measured, presenting statistical anomalies or simulations rather than definitive proof. But the public rarely sees the nuance. The dramatic framing sticks. Planet 9 becomes a character, enigmatic, almost mythic, rather than simply a data-driven hypothesis. Science fiction has primed many people to embrace the idea of hidden worlds. For decades, writers have imagined rogue planets, shadow dimensions, and isolated civilizations surviving in the cold margins of the solar system. Shows like Doctor Who, Star Trek, and The Expanse occasionally dip into themes involving unknown worlds or distant outposts hidden from casual view. Video games depict icy frontier worlds with mysterious ruins or alien secrets below the surface. Planet 9 brings a fragment of that fictional wonder into real scientific discourse. Even if the planet, if found, is nothing more than a cold, rocky or icy world, the act of discovery would blur the line between science fiction and reality in a way that excites audiences. There is also a nostalgic layer to the fascination. Many people grew up learning about Pluto as the 9th planet, memorizing it in school and seeing it on classroom posters. When Pluto was reclassified as a dwarf planet, some felt a sense of loss, even betrayal. Planet 9 offers a symbolic replacement, a way to restore the familiar 9-planet solar system layout, even if the new 9th planet would be nothing like Pluto. This sentimentality isn't scientific, but culture often blends emotion with discovery. In some ways, the search for Planet 9 is partly fueled by the desire to regain something that felt taken away. The visual aspect of the search also plays a role. Artists produce striking renderings of what Planet 9 might look like: a frozen blue orb reflecting dim sunlight, a dark world wrapped in storms, or a rocky sphere covered in frost and shadows. These images circulate widely online, giving shape to something that doesn't yet have observable features. People share them on social media, use them as thumbnails for videos, and incorporate them into documentaries. These visuals build a collective picture of Planet 9 even before its existence is confirmed. When people imagine something vividly, it becomes easier to believe in its reality. Planetary competition adds another dimension. The idea that a single astronomer or a small research team could discover a new planet in the modern era carries enormous prestige. Mike Brown, already well known for his role in the discoveries that led to Pluto's reclassification, has openly joked that finding Planet 9 would make up for demoting Pluto. Other astronomers have different motivations but share the same drive for scientific accomplishment. In the public's eyes, this competition adds drama. It's like following a race with high stakes, where each new discovery or false alarm feels like a plot twist. Culturally, Planet 9 also speaks to deeper themes about the unknown. Humans are drawn to mystery, not just in science, but in storytelling, religion, and art. Hidden worlds, whether literal or metaphorical, appear everywhere in mythology. From the lost city of Atlantis to Shangri-La to the hidden kingdoms in folklore, the idea of something significant existing just out of reach is a recurring pattern. Planet 9 echoes those ancient stories in a modern scientific form. Instead of a city beneath the sea or a kingdom beyond the mountains, it's a world beyond the known planets. The psychological appeal is the same, the promise that there's more to the universe than what we already see. Another reason the public stays attached to the idea is that it arrives in contrast to the increasingly data-saturated world we live in. Most scientific discoveries today are incremental: a new material with slightly improved properties, a slight refinement to a genetic pathway, or a subtle confirmation of a cosmological parameter. Planet 9, by contrast, feels monumental. It's not a 1% improvement in understanding. It's a new world. The sheer scale of such a discovery resonates with people craving big, exciting news. It would be one of the most significant astronomical discoveries of the century, a tangible object that changes textbooks overnight. Social media further accelerates the fascination. Short videos explaining the Planet 9 hypothesis routinely gather millions of views. Influencers in science communication produce animations showing its possible orbit or discussing the latest research papers. These videos blend entertainment with education, feeding the ongoing interest. Even speculative content, like discussions about whether Planet 9 could host moons or what its surface might look like, keeps the topic alive. People enjoy imagining what could be out there, even if the speculation outpaces the data. There's also a philosophical undertone to the fascination. The idea that a massive planet could exist undetected challenges assumptions about how much we truly know. It humbles us. It suggests that the universe is still vast enough, still mysterious enough, that we haven't come close to exhausting its secrets. For many people, that's comforting. In a time when Earth feels mapped, measured, and monitored, space remains the ultimate unknown. Planet 9, whether real or not, symbolizes that wilderness. The search even intersects with fears and conspiracies. Some fringe groups speculate about hidden planets causing cataclysms, reviving old pseudoscientific claims about a Planet X that threatens Earth. While these ideas have no scientific basis, their persistence shows how eagerly people latch onto the concept of unseen worlds influencing our lives. The real scientific Planet 9 often gets tangled with these myths, further embedding it into cultural consciousness. The fascination endures because the story isn't finished. There is suspense built into the search. New data could arrive tomorrow, or next year, or in a decade. A telescope could pick up a faint moving point of light that changes everything. Or it might never be found, pushing scientists to refine their theories and inspiring even more speculation. Either way, the uncertainty keeps people engaged. As long as Planet 9 remains possible, it remains compelling. At its core, the cultural fascination with Planet 9 is a fascination with discovery itself. It reflects our desire to explore, to question, and to push against the boundaries of what we know. Whether the planet exists or not, the search demonstrates something essential about humanity. We are always looking for the next hidden world. The economic and political realities of modern astronomy. Behind the scientific debates and cultural fascination lies a more mundane reality. Astronomy costs money. Telescopes, surveys, computer simulations, and researcher salaries all require funding, and that funding comes from governments, universities, and private donors. The search for Planet 9 is no exception. It's supported by grants from agencies like NASA and the National Science Foundation in the United States, along with contributions from international partners. These grants are competitive, and researchers have to make a compelling case that their projects are worth funding over other proposals. Even exciting ideas must survive the bureaucratic, financial, and political gauntlet that determines which scientific paths move forward. The Vera C. Rubin Observatory, which is expected to play a major role in the Planet 9 search, cost over $600 million to build. That's a significant investment, and it wasn't made solely to find Planet 9. Rubin's primary scientific goals include studying dark energy, mapping the Milky Way, and cataloging transient phenomena like supernovae. Planet 9 is a secondary goal, an enticing bonus rather than the driving purpose. This multi-purpose structure is typical of modern astronomy. Major facilities are designed to address multiple scientific questions, spreading the cost across different research communities and increasing the likelihood of securing funding. A single-purpose telescope has become a rarity. The economics simply don't support building massive facilities for narrow goals. Smaller projects focus specifically on Planet 9, like dedicated search programs using existing telescopes, also compete for resources. Telescope time is among the most precious commodities in astronomy. There are far more proposals than available observing hours. Committees evaluate proposals by scientific merit, feasibility, and potential impact. A Planet 9 search might be compelling, but it's still competing with proposals to study exoplanets, distant galaxies, neutron star collisions, and everything else the universe offers. Not every proposal gets approved, and many that do receive only a portion of the time requested. Most researchers go into the process accepting that compromise is inevitable. The political realities matter just as much. Funding agencies answer to governments, and governments have shifting priorities. In the United States, NASA's budget fluctuates with political winds, economic conditions, and the priorities of whichever administration is in power. During some administrations, planetary science receives more support. During others, funding shifts toward human spaceflight, Earth science, or technological development. These fluctuations affect what projects advance and which get delayed or cancelled. The Planet 9 search isn't immune to these pressures. If funding tightens, survey operations might slow down, data analysis teams might shrink, and the timeline for finding the planet could stretch out for years. International collaboration is another essential dimension. Astronomy is a global enterprise, and major projects almost always involve researchers, institutions, and governments from multiple countries. The Rubin Observatory, for example, is a collaboration between the United States and Chile, where the telescope is located. European, Asian, and South American institutions will also make heavy use of Rubin's data. Because of this structure, the search for Planet 9 doesn't belong to any single nation. Once Rubin's data stream begins, researchers worldwide will have access to the observations needed to carry the search forward. This openness accelerates discovery but it also means the scientific glory will likely be shared. It's a collective effort shaped by global cooperation, which is both a strength and a source of logistical complexity. Private funding plays an increasingly prominent role in astronomy. Wealthy donors and foundations fund specialized projects, sometimes with more flexibility than government grants. The breakthrough initiatives backed by billionaire Yuri Milner have supported searches for extraterrestrial intelligence, interstellar exploration concepts, and advanced imaging methods. Similar private funding could support Planet 9 searches if a donor was specifically interested in the challenge. But private funding is unpredictable. It often depends on the interests, passions, or whims of individual donors, making it a supplement to public funding rather than a stable replacement. Still, in an era of tight budgets, private contributions can push niche or exploratory projects forward when public funding falls short. There's also the persistent question of return on investment. Taxpayers and policymakers often want to know what they're getting for their money. Basic research, especially research that doesn't lead directly to new technology, medical advances, or economic growth, is a hard sell. The search for Planet 9 offers no immediate practical benefits. It won't solve geopolitical problems, cure diseases, or stimulate industry. Its rewards are intangible, expanding human knowledge, refining our understanding of planetary systems, inspiring future generations, and enriching humanity's cultural and scientific legacy. These benefits are real, but they are difficult to quantify. Advocates must continually argue that curiosity-driven research deserves support, even when more immediate societal needs compete for funding. Despite these challenges, funding for astronomy has remained relatively stable over the past several decades, though it's always a balancing act. The public's fascination with space helps significantly. When missions like the Mars rovers, New Horizons' Pluto flyby, or the James Webb Space Telescope capture attention, they generate excitement that translates into political support for long-term investment in space science. A high-profile discovery like Planet 9 could have similar effects. If confirmed, it would be a headline-dominating moment, likely boosting funding and enthusiasm for future projects. Conversely, a long, expensive search that yields no results might make it harder for astronomers to justify ambitious future surveys. These economic and political considerations also shape how researchers frame their work. Planet 9 is often described not just as a search for a missing planet, but as part of a broader effort to understand the outer solar system, test gravitational theories, and refine models of planetary formation. Framing the project this way makes it easier to justify because it ties the search to multiple areas of scientific value rather than a single outcome. Even if Planet 9 doesn't exist, the data, techniques, and discoveries from the search will still benefit astronomy as a whole. That broader scientific payoff is a major factor in securing ongoing support. Another reality is that astronomy often relies on long-term planning. Projects like Rubin take decades from conception to operation. Careers and research programs must adapt around these timelines. Early career astronomers working on Planet 9 today may not see the final answer until they are well into mid-career. The academic job market adds another layer of pressure. Researchers must publish steadily, secure grants, mentor students, and demonstrate progress, even when the nature of their work involves slow-moving observational campaigns or years of computational modeling. Funding cycles typically last only 3 to 5 years, creating a mismatch between short-term evaluation and long-term scientific goals. The search for Planet 9 also illustrates how scientific priorities influence one another. When a major facility like Rubin comes online, the astronomy community must decide what questions take precedence. Time and resources allocated to the outer solar system might reduce the bandwidth available for other areas, and vice versa. The result is a constant negotiation among subfields, each advocating for its own importance. Planet 9 is fortunate to be both scientifically intriguing and broadly appealing. Questions about missing planets, strange orbits, and the architecture of the solar system naturally capture public interest. That popularity provides researchers with a bit more leverage when arguing for resources. Nonetheless, there are limits. Astronomy competes not only with other scientific fields, but with national priorities as a whole. Economic downturns, shifting political climates, or global crises can drain funding from research. During financial stress, basic science is often among the first areas to feel pressure. If budgets shrink, large-scale surveys like Rubin must decide whether to reduce observing time, delay upgrades, or scale back data processing. Smaller Planet 9-focused projects may face even greater vulnerability, especially if viewed as high-risk or speculative compared to more established research areas. All of this underscores that the search for Planet 9 isn't happening in a vacuum. It's part of a larger ecosystem of scientific activity, shaped by human institutions, financial constraints, shifting priorities, and global collaboration. Understanding these realities adds a layer of complexity to the story. It's not just about orbital mechanics and trans-Neptunian objects. It's about how society chooses to invest in the pursuit of knowledge. The search for Planet 9 becomes, in that sense, a reflection of our collective willingness to support ambitious, curiosity-driven science. It's a test not only of our astronomical models, but of our ability to organize, fund, and sustain long-term exploration in a world where resources are finite and priorities always changing. What the latest data really shows. The latest data shows a picture that's tantalizing but incomplete. There's enough evidence to keep the search going and to justify the resources being devoted to it, but there's not enough to declare victory. Planet 9 remains in that liminal state between hypothesis and confirmed discovery, and that's where it will stay until the next major breakthrough. What complicates things further is how slowly the outer solar system reveals its secrets. Unlike the inner planets, where orbital periods are measured in months or years, Itonos take centuries or even millennia to complete a single orbit. That means we're always working with fragments, tiny arcs of motion that have to be extrapolated into full orbital solutions. Small uncertainties in those arcs balloon into large uncertainties when projected outward. Even with good observational data, the margins of error remain stubbornly large. This is one of the reasons why the significance of the clustering is so fiercely debated. The data simply isn't as precise as anyone would like. Another challenge is the uneven coverage of the sky. Most of the deep surveys that have discovered Itonos focus on specific regions, often chosen because they're convenient to observe or lie near the ecliptic plane. That creates gaps, vast swathes of sky, where we simply have not looked closely enough. Planet 9 could easily be hiding in one of these gaps. While surveys like DS, OSOS and PAN-STARRS have improved coverage, it remains far from uniform. This patchiness makes it hard to say with confidence whether the true distribution of ET-NOS is genuinely clustered or simply appears to be because we haven't looked everywhere equally. There's also been new work on how Planet 9 would influence not just orbital clustering, but also the population ratios of distant objects. Some models show that a Planet 9 mass body would create a reservoir of high perihelion objects that rarely approach Neptune, precisely the kind we've been finding more of recently. The ratio of detached objects to scattered disk objects has been inching in the direction predicted by Planet 9 simulations. But the uncertainties are large, and skeptics argue that this trend could be a coincidence or the result of yet undiscovered observational biases. Still, it's another small piece of evidence, nudging the scales, even if only slightly. More advanced numerical simulations have also become an important part of the discussion. Early Planet 9 models tended to be simplified, focusing mainly on ET-NO clustering. Now researchers are incorporating increasingly sophisticated elements, realistic initial conditions for the early solar system, improved treatments of Neptune's migration, and even the effects of the galactic tide. Some of these newer simulations suggest that Planet 9 can reproduce several observed features simultaneously: the clustering, the orbital tilt, the proportion of detached objects, and even the distribution of orbital eccentricities across distant populations. It's this coherence across multiple datasets that many Planet 9 supporters find compelling. A single mechanism producing multiple different signatures is typically more persuasive than one that explains only one feature in isolation. On the other hand, some competing models are getting more sophisticated as well. A handful of researchers argue that instead of a single massive planet, the combined gravitational effects of many smaller bodies, perhaps an extended disk of objects several times more massive than the Kuiper belt, could produce similar orbital patterns. This self-gravity of the trans-Neptunian disk model requires a large amount of mass in the outer solar system, far more than current observations support. But its proponents argue that we might be underestimating the mass of these remote regions, simply because we've only detected the brightest objects. Others have suggested that a passing star in the Sun's early history could have tipped the outer solar system, producing the observed tilt without requiring a hidden planet. These alternative hypotheses each solve part of the puzzle, but none of them provide a clean, all-encompassing explanation. As a result, the debate continues. Then there's the question of Planet 9's visibility, which remains one of the biggest sticking points. If it exists and fits the predicted parameters, why hasn't it been seen yet? The simple answer is because it's extremely faint. At hundreds of astronomical units away, a super-Earth would reflect very little sunlight. Even with powerful telescopes, it might appear as nothing more than a dim, slow-moving speck, easily lost in the background. Some estimates suggest that if Planet 9 is currently near aphelion, the farthest point in its orbit, it could be as faint as magnitude 25 or 26, pushing the limits of current instruments. Rubin's LSST, with its deep repeated imaging of the sky, should be capable of detecting such an object, but only after accumulating enough passes to see its slow motion. Interestingly, infrared searches have also been part of the effort. A planet with several Earth masses should emit faint thermal radiation. Surveys like WISE have looked for such signatures, but their sensitivity drops sharply at large distances. If Planet 9 is colder or smaller than expected, or simply too far away, it could easily evade detection. More sensitive infrared missions planned for the 2030s might finally settle that part of the question. But for now, the infrared data is inconclusive. A related topic gaining attention is the possibility that Planet 9 could be slightly different from current assumptions, maybe smaller, maybe darker, maybe in a more unusual orbit. A few researchers have explored variants such as a sub-Neptune with a large atmosphere, or a rocky super-Earth with an unusually dark surface, or even a dwarf planet-sized object on a more extreme orbit. These alternative models don't fit the ETNO clustering quite as elegantly as the standard Planet 9 hypothesis, but they highlight how sensitive the predictions are to underlying assumptions. If Planet 9 is real, it may not be exactly the kind of world we expect. Despite all this, the optimism among many researchers hasn't waned. What keeps the search alive is the convergence of multiple independent clues, the orbital clustering, the inclination distribution, the solar system's tilt, the population ratios, and the results of dynamic simulations. None of these pieces are individually conclusive, but taken together, they form a pattern that's hard to dismiss. It's the kind of situation scientists often encounter at the edge of discovery, plenty of hints, no confirmation, and the sense that the answer is just out of reach. At the same time, skeptics play an essential role in sharpening the arguments and ensuring that assumptions are challenged rigorously. Their critiques have forced Planet 9 supporters to refine their models, improve their statistical methods, and consider alternative explanations. In that sense, the debate itself has improved the overall quality of research on the outer solar system. The latest data tells us that the case for Planet 9 is neither proven nor disproven. It remains one of the most compelling open questions in modern astronomy, a mystery whose resolution will depend on better surveys, better data, and perhaps a bit of luck. Whether the final answer points toward a hidden planet or a deeper understanding of orbital dynamics, the next few years will be decisive. The implications for exoplanetary science. One of the underappreciated aspects of the Planet 9 search is its relevance to exoplanets. Over the past 3 decades, astronomers have discovered thousands of planets orbiting other stars. These exoplanets come in a bewildering variety of sizes, masses, and orbits. Hot Jupiters orbit their stars in mere days. Super-Earths and mini-Neptunes are incredibly common. Some planets orbit in the habitable zone where liquid water could exist. Others are in wildly eccentric orbits or tilted at extreme angles. The diversity is staggering and has forced astronomers to rethink planet formation theory. One lesson from exoplanet studies is that planetary systems are dynamic. Planets migrate, interact gravitationally, and sometimes get ejected. The neat, orderly solar system we see today isn't the norm. It's one outcome among many possible configurations. Planet 9, if it exists, would be a local example of this dynamism. It would show that even our solar system underwent significant rearrangement, with a planet being scattered into a distant orbit. That makes the solar system more typical, not less, which is oddly reassuring. Super-Earths and mini-Neptunes are particularly relevant. These planets, with masses between 1 and 10 Earth masses, are the most common type in the galaxy. They're found around stars of all types, from red dwarfs to sun-like stars. Yet the solar system doesn't have any between Earth at 1 Earth mass and Uranus at 14.5 Earth masses. That's a conspicuous gap. Astronomers have speculated about why it exists. Maybe the conditions in the solar system weren't conducive to forming super-Earths. Maybe they formed but were disrupted or ejected. Planet 9, with an estimated mass of 5 to 7 Earth masses, would fill that gap perfectly. Finding Planet 9 would provide a natural laboratory for studying super-Earth properties. Most exoplanets are too far away to study in detail. We can measure their mass and orbit, and for some, we can study their atmospheres using spectroscopy. But that's about it. Planet 9 would be close enough to observe with much greater precision. We could study its composition, atmosphere, surface, if it has one, and thermal properties. That data would inform models of super-Earth formation and evolution, helping us understand the thousands of similar planets orbiting other stars. There's also the question of planetary habitability. Super-Earths in the habitable zones of their stars are prime candidates for hosting life. Understanding how these planets form and what they're made of is crucial for assessing their potential habitability. Planet 9 is far too cold and distant to be habitable, but studying it would reveal details about super-Earth interiors, atmospheres, and magnetic fields that are relevant to habitable zone planets. It's a stepping stone, a nearby example that we can study in detail to inform our search for life elsewhere. The dynamics of Planet 9's formation and evolution also parallel what we see in exoplanetary systems. Many exoplanets are in orbits that suggest they've migrated or been scattered. Hot Jupiters, for instance, couldn't have formed where they are. They must have migrated inward from farther out. Understanding how and why planets migrate in our solar system helps us model migration in other systems. Planet 9's history, if we can piece it together, would be a case study in planetary scattering and dynamical instability. There's also the possibility that Planet 9-like worlds are common. If our solar system has one, maybe others do too. Detecting these distant planets around other stars is incredibly difficult. They're faint, far from their stars, and take centuries or millennia to complete orbits. Current exoplanet detection methods are biased toward finding planets close to their stars. But future telescopes and techniques might be able to detect distant giant planets, and Planet 9 would give us a template for what to look for. The connection to exoplanets also highlights the importance of the Planet 9 search beyond just filling in the solar system map. It's about understanding how planetary systems work in general. The solar system is the only one we can study in extreme detail, with spacecraft visiting planets and moons, and long-term monitoring of orbits. Discoveries here inform our understanding of the thousands of systems we can only glimpse from afar. Planet 9 is a piece of that larger puzzle. The search for Planet 9 has driven advances in observational techniques and data analysis that benefit exoplanet science. The algorithms developed to detect slow-moving distant objects can be adapted to find faint exoplanets. The statistical methods used to assess clustering and biases are applicable to exoplanet population studies. The simulations that model Planet 9's effects on the outer solar system use the same computational tools that model exoplanetary system dynamics. Progress in one field feeds into the other, creating a virtuous cycle of discovery and understanding. Another fascinating angle is how Planet 9 might validate or challenge existing migration models. Many exoplanetary systems contain planets in resonances or in compact multi-planet chains where gravitational interactions dominate their long-term evolution. If Planet 9 formed closer to the Sun and was later kicked outward, that implies a dramatic reorganization phase early in solar system history. This would align the solar system with what we see elsewhere, a place where early chaos leads to later stability. Understanding that process in our backyard would let astronomers refine simulations of exoplanet evolution, helping explain why some systems remain orderly while others become wildly unstable. There's also a broader philosophical consequence. For years, astronomers wondered why the solar system seemed so special, lacking the common planet types found around other stars. If Planet 9 turns out to be a super-Earth, it removes a major oddity. Suddenly, the solar system looks less like an exception and more like a typical middle-of-the-road system, with all the familiar components simply arranged in a more spread-out pattern. That shift in perspective matters because it affects how we interpret exoplanet data, whether we treat the solar system as a baseline or an outlier. Planet 9 also pushes the limits of observational astronomy in ways that mirror challenges in exoplanet detection. Trying to detect an extremely faint object against the brightness of the Milky Way is similar to trying to detect an exoplanet hidden in the glare of its star. Techniques like stacking exposures, improving noise reduction, refining sky subtraction, and using machine learning to identify subtle movement patterns all contribute to improving both fields. In that sense, the Planet 9 search is almost a training ground for the next generation of exoplanet detection methods. Finally, there's the narrative element, the way Planet 9 bridges two worlds of astronomy that often feel separate. The outer solar system used to be considered quiet, cold, and relatively uneventful. Exoplanet science, meanwhile, was seen as dynamic, chaotic, full of surprises. Planet 9 connects these ideas. It suggests that even our own system may have a far more dramatic history than we once thought, shaped by gravitational battles, migrations, and near-catastrophic rearrangements. It turns the outer solar system from a static afterthought into a frontier packed with clues about cosmic evolution. Why the search matters. The search for Planet 9 has become one of the defining quests of 21st century astronomy. For nearly a decade, it's occupied the minds of researchers, captivated the public, and pushed the boundaries of observational and theoretical techniques. Whether Planet 9 exists or not, the journey has been extraordinary. We've mapped the outer solar system in unprecedented detail, discovered dozens of new trans-Neptunian objects, and gained insights into how planetary systems evolve over billions of years. The hunt has reminded us that even in our cosmic backyard, mysteries remain. If Planet 9 is found in the next few years, it will be a triumph, a validation of mathematical prediction and patient observation. It will reshape textbooks, inspire a new generation of astronomers, and open up entirely new avenues of research. The planet itself will become a target for decades of study, with missions eventually planned to visit it and reveal its secrets up close. We'll learn about its formation, its composition, and its role in sculpting the outer solar system into the configuration we see today. If Planet 9 isn't found, that too will tell us something important. It will mean the clustering of trans-Neptunian objects has a different explanation, one we haven't fully understood yet. It will push us to refine our models, reconsider our assumptions, and look at the data with fresh eyes. Science advances through both confirmations and refutations, and either outcome moves us closer to understanding the truth about our solar system's architecture. The story of Planet 9 is far from over. The Vera C. Rubin Observatory will soon begin its comprehensive survey of the southern sky, bringing unprecedented sensitivity to the search. New ETNOs will be discovered, orbits will be refined, and the statistical picture will become clearer. Within a few years, we'll likely have a definitive answer one way or another. Until then, the mystery endures, reminding us that the universe still has the power to surprise us, to challenge our understanding, and to reward those patient enough to keep searching. The hunt for Planet 9 continues, and somewhere in the darkness beyond Neptune, the answer is waiting to be found.